So hello and welcome to your neuron platform Physics Wala. This is your physics mentor Gaurav Tiwari, and today, my dear kids, we'll be focusing our understanding on the chapter of current electricity, where the charged particles are going to move miraculously. Right? We will start our understanding from the basic concepts of drift velocity and Ohm's law. Then we will move toward the second part, where we will talk about the circuit solving. We consider this part as the hero of the chapter, and then we will talk about the third part, where we will discuss the application side of it. Right? So if you cover all these three segments, these three parts of the chapter, you will find that every single concept of this chapter is clear in your brain. And after that, for the practice, you can download the DPP I'm going to share with you, right, through the link given in the description. Right? You will find that PW is revolutionizing the way we learn, and this channel is just one more pure effort in the same line of action. Right? Let us start this chapter right away without any further delay. Let's go. Now, my dear kids, if you go on NTA website like a normal kid and go on the syllabus like a normal kid and then choose a chapter of current electricity, because that's what we are going to do, and see in it that there are these topics that are mentioned under the syllabus on the NTA website. So these are the topics that you have to cover no matter what. Now, what I have done, I have picked those topics and make a list out of them, right? Now, the best way to cover anything is divide them into segments. And as I have already told you that we have divided every topic given in that list of the NTA syllabus, right? So I have divided everything into three segments, right? So in these three segments, every topic will be covered. In the first segment, we will talk about the fundamental concepts, right? These are very, very important. And many times you will find that a question is asked from this simple first part, right? Do that without any further problem in your brain, right? Now, the second part is circuit solving with tricks. There are a lot of tricks that I'll be telling you in the circuit solving part, and after that, you will find that circuit solving is easy, nothing that difficult, nothing that complicated. And at the last, we have the application of the concepts. We will be discussing about the Metre Bridge and the combination of cells and all those things, right? So miscellaneous concepts will be there in the last part, right? So if you cover these three parts, you will find that every concept that was asked in the NEET paper, right, is there in your brain as well, right? And after that, you just have to go through the DPP, right? Let's start right away with the first part, right? Have a look at that. These are the topics of the first part. Let's talk about the electric current. What is electric current, my dear kids? Electric current talks about the rate of something, right? Not the amount of something. So what is the difference between rate of something? Rate of something means how quickly something is done, right? For example, if I lift 100 kilos, right, or let's say if I do 100 joules of work and somebody is doing 1000 joules of work, right, we are not talking about the total amount, right? I am doing 100 joules of work in 2 seconds and somebody is doing 1000 joules of work in, let's say, 1000 seconds, right? So every second I am doing more work, 50 joules per second, and he is only doing 1 joule per second, right? So I am doing more work. So my rate of work is higher. So whenever we talk about rate of something means how quickly something is happening, right? So rate of, what is the electric current? It is the rate of flow of charge, not the amount of charge. It is the rate of flow of charge. That means how quickly the charge is flowing, right? So current is rate of flow of charge. So for simple grade 9th definition is this: I is Q by T. We will talk about more in later pages, right? So I is Q by T, how quickly the current charges are flowing, right? Now you see that there are two interpretations of the current, right? Now you see that here the positive charges are flowing, here the negative charges are flowing. What is the meaning of that? Earlier, before we discovered the concept of electrons, right, we had no idea about the electrons. We thought that the electric current is flowing due to the positive charges, right? So of course, it is flowing from the positive terminal because the positive charges are here towards the negative terminal, right? Because the negative will attract the positive. So it is what we used to think, that that's how the current flows. Current is flowing from positive end to the negative end due to the flow of positive charges, right? We call this current as conventional current. What did we call it? We call it conventional current. Conventional current. We said the current is flowing due to the flow of positive charges, right, from the positive terminal to the negative terminal. We called positive terminal at the higher potential and negative terminal at the lower potential. These things were well established, right? But later on we find out that it is not the positive charge that flows. Electrons are flowing. The flow of electron causes the current, right? So instead of correcting everything under the sun, we said, okay, right, electrons are making up the current, right? Positive is still we call the higher potential, negative is still called the lower potential. But we just said that, okay, negative charges are flowing, right? Electrons are flowing and making the current. So electrons will flow toward the positive terminal. So yeah, this is how the electrons are flowing, right? And we kept the current's direction same. We followed the same direction of current. We said that, okay, current direction is opposite to the flow of electron, right? Current is not due to the positive charges, right? So conventional current, we kept the direction of the conventional current, which is in the flow of the positive charges, right? And we simply said that the current is assumed to be opposite to the flow of positive charges, right? Current is assumed to be opposite to the flow of, negative charges, right? It is in the direction of the positive charges, right? So this is what we assumed, right? So the current due to the positive charge is called as conventional current. This is called as electronic current, or we can say simply due to the electrons, right? But what we assume is the current is always flowing to the in the same direction of the positive charges, right? But the reality, you know, right? Okay, so a current is dq by dt, delta q upon delta t, right? The unit of current is going to be ampere, right? So there are two variations of the current: average current and instantaneous current, right? Average current and instantaneous current. Average current is, you know, that whenever the time interval is taken as huge, for example, in the 50-second interval, right, for the first 10 seconds current was rising, then for the next 20 seconds the current was flat, then the current starts falling. So you see that here I am talking about the larger intervals, right? Here the current was rising, so the value of current was something else. Here the value of current was something else, and the last part the value of current was something else, right? Was reducing, right? But if I have to tell you what was the current flowing in the 50-second interval, right? So in that case, I will talk about the total charge flown in that whole 50-second frame upon the total time taken, which is the 50 seconds, right? That will give me the average value, average current, right? In that entire duration, some coulomb of charge will be flowing through the conductor, right? If I take all that charge and write it on the top, right? And if I divide it by the total duration, so I will get the average current, right? Delta Q upon delta T, current flowing for a larger time interval, is the average current. Instantaneous current is how much current was flowing at an instant. So in the 50-second journey, if I have to tell you how much current was flowing at 13th second, so that is, I am discussing about the instantaneous current. Here what is happening, the time interval I have reduced. I am not taking the entire 50 seconds the time interval. I have reduced the observation period to just that second, right? So what is happening? The time interval is reducing to 0. I am talking about that very instant. So delta t is very small, right? So right now I'm talking about not at an average time span. I'm talking about the instantaneous time span. So here it is going to be dq by dt, right? Okay. Now, once you know the value of current, so you see that delta q is here. If you take the delta t over there, so what will happen? I is dq by dt. I is dq by dt, right? So from here, you can say if you want to get dq, it will be I dt, integrate it, you will get a total charge flowing through the conductor. Now, what is Ohm's law, right? Simply let us talk about the Ohm's law. What is Ohm's law? Ohm's law tells you the relation between the applied voltage and the current that it will bring to the circuit, right? Okay. You see that? Here what is happening? Let us say that I have a resistor, right? And let us remove all the switch and ammeter and voltmeter from the circuit for a second, right? Just take a very simple circuit. I am connecting it with a single cell, right? The single cell has a potential difference of V. It is offering the current I through the conductor, right? I found that if I connect another cell in this fashion, so what is happening? I have effectively increased the potential difference, right? Earlier I had 1.5 volt battery. Now I have two batteries side by side. So I have 3 volt net potential difference, right? So potential difference is increased. I found that the current is increased as well. And whatever resistance was there, now it is getting more current, right? Similarly, I have attached another battery. So the potential difference is increased further. And that has increased the value of current even further. Similarly, I have done the same thing again. The current is increasing again. Voltage is increased further, current is increasing further. So what is happening? These two things are following a sense of proportionality, right? So through this resistance, what is happening? Voltage and current are found to be proportional to each other, right? Now, unnecessary debates are also there. I is proportional to V or V is proportional to I, but we don't need that, right? We have found that increasing the voltage across the same resistance brings more current through it, right? So V is proportional to I. And if you remove the proportionality constant sign, the constant will come into the picture, that is R, right? So V is equals to R into I, or you can say the resistance is the ratio of voltage and the current across the resistor, right? Okay. All right. The unit of resistance is ohm, right? Now, what are the factors on which the resistance depends? So you see that the resistance is basically rho L upon A, right? Rho is called as the resistivity of the material, right? It depends on few more things. We will talk about that in upcoming part. So this is called resistivity of the material. What is this? Resistivity. What is L? L is the length of the conductor. And what is A? Area of cross section. Cross sectional area of the conductor, right? So if you just put them together, R is rho L upon A, this is what you're going to get, right? So here you can see that increasing the length will increase the resistance and making the wire thicker will reduce the resistance. Here we will not change the material of the conductor. So rho will remain same and we will not change the temperature and other things of the conductor, right? So that we will keep same for now. But right now what is happening? We are only affecting the geometry, that is length or cross sectional area of the conductor, right? So let's move ahead. Now here you have seen it, right? Now the opposite of resistivity, right, is called as conductivity. Electrical conductivity. So conductivity is 1 upon resistivity, right? So here you have seen it. R is rho L upon A. So what is rho? Resistivity is R A upon L. So just invert it. So 1 upon rho is L upon RA. Just invert it. Rho is RA upon L. 1 upon rho will be L upon RA. So that will give you the conductivity. Opposite of resistivity is conductivity. It tells you how conductive a given material is, right? Very simple. Okay. Now, this is a very interesting kind of problem, and these kind of problems are asked multiple times in your exam, right? The type of problem is called as wire stretching problem. Now, what will happen? As a kid, you might have done this thing that you are chewing a chewing gum, right? And when you stretch it, the chewing gum goes thinner and longer, right? So what is happening? You had a wire. Now you are stretching the wire. So when you are stretching it, the length will increase, but the cross-sectional area, the thickness will reduce, right? Yes or no? So this is the original length. Let's call it L1. And let's say you have stretched it n times. So the second length is n times of original length, L1, right? Okay. Because of increasing the length, the cross-sectional area will reduce. So initially, the cross-sectional area was A1. And now the cross-sectional area has been changed. It is now A2. My dear kids, we are not introducing any new material. So what will happen? The volume occupied by the wire will remain same in both the cases. So if I just do that, volume previously was A1 into L1, right? This was the initial volume. And finally, the area is A2 and the length is L2. This is the final volume. The volume is not changing. So it will become like this, right? Okay. A1, L1 will become same as A2, L2. Okay. Right. Now you are saying that the length has been increased to n times of original length, right? So let's do that. L2 is n times of original length. So A1, L1, and instead of L2, it is n times L1, right? So clearly, I can say that A2 will be A1 upon n, right? So if you increase the length by n times, right, you see that the area of cross section will become 1 upon n times, right? Okay. Now, due to this, what will be the effect on the resistance? Initially, the resistance of the initial wire was rho L1 upon A1, right? What will be the new resistance? New resistance will be rho L2 upon A2, right? Now, instead of L2, you can say L2 is n times of original length. So, rho n times of original length upon A2. The A2, the cross-sectional area is A1 upon n. A1 upon n. This n will go in the numerator and it will become n square, rho L1 upon A1. My dear kids, rho L1 upon A1 was the original resistance of the wire R1. So instead of this part, you can put R1. So R2 will be N square times R1. I believe the idea is very, very clear, right? So what is happening? If you increase the wire, if you increase the length of the wire n times, what will happen? The resistance of the wire will become n square times. If you increase the length of the wire by n times, the resistance of the wire will become n square times, right? So I believe the idea is very, very clear, right? Okay, so it's a very interesting observation, right? So let's do that. If the wire is stretched to the double of its length, find the new resistance, right? Find the new resistance if the original resistance of the wire is R. So what is happening? We are doubling the length of the wire. What will be the new resistance? So let us do that with the help of, a conventional way. But right now we know that if you increase the wire length by n times, if the length of the wire is n times, right, the resistance will become n square times the original value, right? So wire length is doubled, the resistance will become a square of double, which is 2 square, which is 4. So clearly the resistance will become 4 times, right? But let us do that conventionally as well and see if our conclusion is correct, right? So right now what is happening? We can say the volume will remain same upon stretching, right? So wire is stretched to double its length. So the L2 is 2 times of L1. 2 times of L1, right? So you see that the second area, the area in the second case is half of the area in the original case, right? So the new resistance is going to be rho L2 upon A2. L2 is 2 times of L1 and A2 is A1 by 2. So 2 will go up. So it is 4 times rho L1 upon A1. Rho L1 upon A1 is the original resistance. So it is 4 times R1, right? You see that the resistance in the second case is 4 times the original resistance. You see that? This is what we have already concluded. So you don't have to solve all these things if you have simply understood this idea that increasing the length of the wire by n times makes the resistance of the wire n square times, right? So I believe the idea is very, very clear, right? Now look at this question. Consider a wire of length L, area of cross section of resistivity rho, right, with a resistance of 10 ohm. Its length is we are applying a force. Okay, its length is applying a force. Basically, the language of the question needs to be corrected. We need to say that we are applying a force along the length, and it becomes 4 times the original value. So basically, we are applying a force along the length, and the length of the wire becomes 4 times the original value. If the original length was L, now we have made it 4 times L, right? Find the change in the resistance of the wire. So clearly, by common sense, we say that if the length is becoming n times, 4 times, right? So the resistance will become n square times. So 16 times of original resistance, right? Original resistance was R. So it will be 16 times of original resistance, right? So original resistance was 10 ohm. This time will be 16 times of 10, which is 160. So without any problem, we have solved it. But through the conventional way, I can also show you, right? In the exam, you can directly click, tick the option and move ahead. But just to show you that this method is always working, I'll show you the conventional method as well. Right now, you will say that stretching will not change the area of the length, volume of the wire. A1 L1 equals to A2 L2, right? So you see that the length is made 4 times, right? So A1 L1 is A2 4 times L1. So A2 is going to be A1 by 4. I believe the idea is very, very clear, right? And when the area is A1 by 4, what will happen? The resistance now, R2 is rho L2 upon A2, right? So what is going to happen? Rho L2 is 4 times L1 and A2 is, here you have just seen A1 by 4. The 4 will go up. It will become 16 rho L1 upon A1, which is 16 times R1, right? 16 times R1. Original value of R1 was 10. It is 160. ohm, right? So I believe the idea is very, very clear, right? We don't have to solve all of that in the exam. Doing simply this observation is enough, right? It will give you the correct option by default, right? So now let's move on and talk about the next one. The resistance of the wire 2 ohm is to be made from a copper wire with a specific resistance this much. Using a wire length of 50 centimeter, what should be the radius of the wire? So you have to design a wire that can give you the required resistance, right? You know that R is equals to rho L upon A, right? A is the cross-sectional area. So rho L upon, let's say the cross-sectional radius of the wire is a small r. So pi r square will be the area, right? So pi r square is rho L upon capital R. So r square is rho L upon pi r. So small r is, right, rho L upon pi r, pi capital R, sorry, right, rho L upon pi r. Okay, I'm just taking this pi to this side. So r will be under root rho L upon pi r. So I believe the idea is very, very clear. Right. So instead, just place the value of rho over here. There is a specific resistance rho. Just put the value of length, which is given in the question. The length of the wire is 50. The value of pi you can put approximately 3, and value of r you can also put as the resistance of the wire is 2 ohm. Just 2 ohm. Just put the values. This is for you, right? And you can solve it. You will get the value of radius of the wire that will be needed to make this wire. Right. Now you have this question: a nichrome wire of 1 meter long and 1 mm square in cross sectional area is drawing a current of 4 ampere at 2 volt. The resistivity of the nichrome is. What will be the resistivity of the nichrome? So again, very simple part. You can easily solve that one as well. So nichrome wire is 1 meter long. So the length of the wire is 1 meter. Right. The area of cross section is 1 mm square. So the area of cross section is 1 mm square. So you also have to convert it into, meter square. So what will you do? Right, 1 meter has 10 to the power 3 millimeter. So here you have to multiply by 10 to the power minus 6 meter square, right? I believe the idea is very, very clear. Right. And now you see that it is drawing a current of 4 ampere at 2 volt. So the current it is drawing is 4 ampere and the voltage that is drawing the current at is 2 volts, right? What will be the resistivity of the nichrome wire? You have to talk about the resistivity of the nichrome wire. So resistivity is rho. You have to talk about that. So I and V are given. So from that, resistance of the wire can be calculated. V equals to IR, right? So R equals to V by I, right? So V by I, right? V is 2, I is 4. So 2 by 4 is going to be 0.5 ohm. This is going to be the resistance of the wire, right? Now you know that R equals to rho L upon A, right? You have to find the value of rho. Resistance you have already calculated. It is 0.5, right? V by I. Length it is already given 1 meter. And area of cross section is 1 mm square, which is this, right? You just have to find the value of rho. This is easily you can find, right? Now let us move on and talk about the next part, which is this. A resistance of the wire is R1 that is drawn out so that the length is increased by twice of the original length, right? Length becomes twice the original length. The ratio of new resistance to the original resistance is. So clearly you can say that because the length is becoming 2 times, right? The L2 is 4 times the original length. So what will happen? If the length becomes n times, resistance becomes n square times. That is 2 square times, which is 4 times, right? So again, we have done that multiple times conventionally, right? The ratio of new resistance to the original. So R2 upon R1 we have to answer. That is going to be 4:1, right? So I believe the idea is very, very clear, right? It's going to be 2:1, right? So here in this solution, they have taken the resistance, length as 3 times, which is why they are coming out 9 times. But here in the question, it is written that we have to make it twice of the original length. So it's a printing error. No problem, but the idea is going to be same, right? The resistance of the wire is 5 ohm. Its new resistance in ohm, if it is stretched to 5 times the original length. So if you are stretching 5 times the original length, you see that L2 is becoming 5 times the original value. So R2 will become, right, N square times the original value, right? So N square is 5 square. So it is 25 times the original value. I believe the idea is very, very clear, right? So original value was 5 ohm. So multiply that, it is 125 ohm, right? So the original, the new resistance will be 125 ohm. Option C is going to be correct, right? Now let us talk about the current flowing through the conductor. Let's understand the current itself, right? Because now we are going to enter and talk about the drift, velocity, and all those things. And to understand that, we have to talk about what actually happens when the current is flowing through a conductor, right? Let's talk about that. Here you can see some charged particles are there, right? And we have seen that the current will exist only due to the movement of charged particles, right? But we have found that there are two possibilities that will cause the movement of charged particles, right? What is those two possibilities? There are two possibilities that will move the charged particle. First is the charged particles will move due to the heat. It is thermal motion, right? Thermal energy, right? Or we can say thermal agitation. And the second kind of movement is due to the electric field, external electric field, right? Okay, so the first possibility due to which the charged particle will move is due to the environmental heat or any other heat that you are giving to this particular conductor. This is the first thing that will move the charged particle. And the second possibility that will make the charged particle move is the electric field, the external field that you have applied, right? Okay. If you do these two things, then the charged particle, we can have a better understanding of the charged particle that we have in the hand, right? Now we have understood that the thermal, if when you give the heat, or you can say the charged particles getting heat from the atmosphere, right, that will bring no current. The current due to this thermal motion is zero. Why so? Because if I take any particular cross-sectional area like this, so the thermal motion is entirely random. So we have found out that, let's say, if 100 electron, let's say this is the cross section, at randomly chosen cross section, 100 electrons are crossing due to the thermal motion. 100 electrons are crossing this cross section right now in this way. We found that at that very instant, 100 electrons will be passing the other way as well. So through this section, how many effective number of electrons have crossed? We can say 0. 100 goes this way, 100 goes this way. So effectively, through this section, no net flow of charge is taking place. So through this section, no net current is taking place. And same goes on for all the sections, right? Doesn't matter where you take the section, there is no net flow of charge through any given section, and which is why we can say that due to the thermal motion, no current is contributed to the circuit, right? Okay. But when you apply the external field, what happens? When you apply the external field, then what happens? Let's say to set up the external field, you need potential difference. One end will be at higher potential, positive, let's call it higher potential. And one end will be at lower potential, let's call it negative. So external field will set up from positive to negative. This is how the external field will set up, right? External field will set up from positive to negative, right? Now this external field will do interesting things. This external field will, pull the negative, these positive charges will try to move towards the negative ones, but the positive charges don't move. It is the electron that move towards the positive terminal, right? So the electrons over here, they all have negative charges. They move toward the positive end or opposite to the external field, right? Okay, like this. So what is happening, right? As soon as you apply the external field, the electrons inside the conductor start feeling a push opposite to the external field, and that causes a net displacement across any given cross section, and that causes the electric current, right? Now think about it. The electrons don't have a straight empty road in front of them, right? They have a lot of other charged particles and other electrons, right? Just like a vehicle is moving through the traffic, cannot move in a straight line, it has to follow a very zigzag curved path, right? The same thing is happening with electrons. It cannot follow a straight line, it has to follow a very zigzag path. And now, due to which we can say that electrons are not moving in a straight line path, they are kind of drifting. Drifting means suddenly changing the directions, right? So electrons are drifting towards the other end, we can say that, right? So what is happening when you apply the external field? Electrons are drifting to the other end, and this drifting motion is what causes the current. We can say that it contributes the current due to the drifting motion. Current due to the drifting motion is not zero, right? It has some value, right? So we can say that there are two for the electric current, we need the charged particles to move. The charged particles are moving due to two things, due to thermal motion and due to the external electric field. But this thermal motion is not contributing to any current, because at any cross section, whatever number of electrons are moving one way, due to the thermal motion, the same number of electrons are considered to be moving the other way, and that is why the thermal motion is not contributing to the current, right? On the other hand, the electric field, external field, is doing this thing. It is whenever you apply the external field on these particular charged particles, the electrons feel a push towards opposite direction of the external field, and that push makes the electron to drift towards the other end, and this drifting of electrons makes creates a current across the conductor, right? So I believe the idea is very, very clear, right? Okay. All right. So when you apply the external field, the drifting starts to happen, right? Okay. All right. So you see that due to the thermal motion, right? Due to the when there is no external field, so the motion is happening, but the motion is called as thermal motion, right? Acha, at absolute zero temperature, this movement will not happen at all, right? Absolute temperature, all the particles will cease to move, right? So what is happening? Due to thermal motion, the electron started over here, and after all that zigzag, it ends over here. So you see that there is no net displacement in or in the direction of electric field or opposite to the electric, or there is no electric field right now. So along the axis of the conductor, there is no net movement, right? So the conductor is electron started over here and ended over here. So the displacement along the conductor is zero, which is why it is not causing any current. But right now, due to the external field, we can say electron started over here, and after drifting, it ended over here. So we can say that effectively it has covered some distance. This is the drift, right? So yeah, due to the external field, we will have some current, right? Okay, so what is drift velocity? The average rate at which the electrons are propagating, electrons are displaced against the electric field. Drift velocity is against the external electric field. So what is drift velocity? The average rate at which electrons are drifting against the external field is the drift velocity, right? It is in the order of millimeter per second. It is very slow, right? Now, how to calculate the drift velocity? Now, have a look at that, right? Focus on any one of these electrons. So I am removing the other circles so that we can focus on any one electron. This one, right? So what is happening on this electron? Due to the external field, a force will be applied. How much force will be applied? We can say how much force will be applied? If the external field is E, the charge on the particle is E, Q. So the force applied will be E into Q, right? Yes or no? This much force is applied, and the mass of the electron is m. So what will happen? It will get an acceleration, right? It will be accelerated. So what will be the acceleration? Force per unit mass. What is force? EQ upon m. Right? This is going to be the acceleration, right? Now think about it. Here, if you just focus, precisely, you will find that these electrons are not moving smoothly from one end to the other end, right? So what is happening? They are drifting. So while they are drifting, they are colliding with the nearby particles. You see that the electrons are moving like this. So they are colliding with the nearby particles like this, right? So when they are colliding with the nearby particles, think about it. Imagine that this electron wants to move opposite to the field from one end to the other end. It will move and it will strike the other particle or something, right? Then it will change the direction. Then again it will strike, it will change the direction. Again it will strike over here, it will change the direction, and things like that. It will continue to move, right? So see that before the first strike could happen, the force was acting on it opposite to the field I have just shown you. This force will accelerate for a time duration, let us say tau 1, right? For this time t1, the particle was accelerated. Then it is colliding, and then again for this duration the particle was accelerated. Again for this duration the particle was accelerated, then it collided again. Again for this duration from here to here the particle was accelerating, and then it collided again, right? So you see that the particle is accelerating for a while and then it collides again to another particle, right? You see that it is not accelerating for the same time interval all the time, right? So the time interval we can take average, right? So we can take average of t1, t2, t3, t4, and we can say there is the average of time interval for which the particle is relaxed, right? Initially, for the time t1, the particle is relaxed. It is not colliding with anything, right? So for t1, the particle was relaxed. It is simply accelerating. Then it is only accelerated for time t2. It was relaxed for time t2. It accelerated for time t2. Then it accelerated for time t3. Then it accelerated for time t4, right? So you see that the particle is not accelerating forever, right? The time it is accelerating for is changing, right? And that is called, if I take the average, it will be called as relaxation time. So relaxation time is the average time for which the particle is accelerating. It is the average of t1, t2, t3, t4, right? Okay. All right. So you see that this is force upon mass. This is the acceleration acting on the charged particle. I have just shown you with a diagram, right? Now, if the particle is accelerating, right, think about it. External field is constant, charge on the electron is constant, so force E into E is constant, right? Mass of the electron is constant, so acceleration will be constant, right? If the particle has a constant acceleration, so what will be the velocity, right? We can say that because we have assumed the relaxation time is tau, right? Relaxation time is tau. Let us say that n collisions are happening in the journey. So what is happening? T1 plus T2 plus T3. Average of all this time will be the relaxation time, right? The average time during which no collision is happening and the particle is accelerating. We can say that that is the relaxation time. So, right. So what is happening? Velocity v equals to u plus at, right? This is, let's say, this is the conductor. And in that conductor, if I just focus on this electron, it was drifting and all like that, right? So we can say that for an average time tau, it was accelerating. Let us say the initial velocity was 0, right? And due to the force, what was the force acting right now? The force acting is E into E upon mass, right? Due to this force, the particle was accelerating. This is the acceleration, right? Due to this force upon mass is acceleration of the particle, E upon m, right? So how much velocity it will achieve after the acceleration? So v equals to u plus at, right? V equals to u plus at. Initial velocity was 0. Acceleration is E upon m, right? And time is relaxation time. So just drift velocity will be E upon m into relaxation time. I believe the idea is very, very clear, right? This part is the mobility mu. Drift velocity is mobility into E, right? So E upon E tau upon m. This is the mobility, right? E is the charge of electron, m is the mass of electron. This is constant. Relaxation time is tau, right? You see that higher relaxation time means particles are not colliding very often. They are accelerating very easily. Now think about it. If you are moving on a highway, you don't have to constantly steer yourself. You can just, accelerate. You will say that the mobility on this highway is very easy. I can easily move on this highway, right? Okay. Relaxation time is higher, so mobility will be higher. So relaxation time means the time for which the particle is assumed to be accelerating only, right? So yeah, so I believe the idea is very, very clear. All right, so yeah, this is it. Drift velocity is mobility into external field. So mobility is depending upon the this particular thing. This is called as tau, right? Now think about it. Mobility is E tau upon m, right? So what are the factors that will affect the mobility? We can say charge and mass of the electron cannot be changed. So drift velocity is depending on mobility depends on the relaxation time. So if the collisions are happening much frequently, the relaxation time will reduce, right? And why the collision will happen much frequently? Because the temperature you may have increased. So if you just increase the temperature, the collision will increase, right? And the relaxation time will reduce. That will reduce the mobility, right? And of course, if you change the material itself, right, will be responsible for changing the mobility, right? Okay. Okay. Now this is another expression for the concept of drift velocity. So what is happening? I is q by t. We know that, right? Let us have a look at that. I is q by t. Current flowing through the conductor is rate of flow of charge q by t. So what is the total charge that is flowing through it? We can say the total charge flowing through the conductor. Let us say the area of the conductor is A, right? And the length of the conductor is L. So this is the total volume, right? Let us say charge in a unit volume of the conductor is N. So volume charge density is N, right? So N is charge per unit volume. This is the total volume. Multiply that. We have the total number of charges inside that volume. Right. Now what is happening? Each of this charge is an electron, right? And each electron has a charge small e. So total number of charges is this. Multiply that by e. We have total charge q, right? Okay. Total charge we have written. And the time is going to be distance upon velocity. So distance is L. And the velocity with which it is moving is Vd. Right. That's it. That's it. Right. So you have I, right? Just solve it and get the value of Vd from here. So what is going to be Vd over here? Vd is going to be, or the current is going to be NEAVD, right? So current is going to be just, this will go up, L and L will cancel out. So NEAVD. It's a very popular formula. The value of current, if we know the value of drift velocity through a conductor upon the application of external field, how much current it will bring to the current circuit or through that conductor, we can say NEAVD. Okay. So over here, we have already seen that what will be the effect of, relaxation time on drift velocity. So we can say that if the relaxation time changes, the drift velocity also changes, right? Because the relaxation time changes the mobility of the conductor. Higher relaxation time means higher mobility, lesser collisions, right? And lesser relaxation times mean more collisions and lesser mobility. And that will of course reduce the drift velocity. So right now you see that drift velocity is E tau upon m, right? So this is very simple. This is the acceleration. This is the acceleration. Force upon mass into acceleration, u plus at, right? So a into t. This is the drift velocity. Mobility is just this proportion. This constant is the mobility, right? Electric field should be out. So E tau upon m is the mobility, right? Okay. Relation between the current and the drift velocity. So current and drift velocity and NEAVD, we have seen it. So these are the three interesting formulas that you have to remember, right? These are the three interesting formulas that you have to remember. Now look at this particular question and try to solve it. Okay. All right. Let's have a look at that. A current of 2 ampere is flowing through a wire of cross-sectional area 25 millimeter square. So current of 2 ampere is flowing. So current of 2 ampere is flowing, right? Through a wire of cross-sectional area 25 mm square. So wire has cross-sectional area of 25 mm square. So that many meters square. The number of free electrons in a cubic meter is this. So the charge density is 2 × 10⁻28, right? Charges per meter cube. The drift velocity of the electron is going to be, so what will be the drift velocity of the electron? what will be the drift velocity of the electron? Now think about it. The value of charge is also given, right? So E equals to 1.6 into 10 to the power minus 19 coulomb, right? So drift velocity you have to find out. I is NEAVD. Right? VD you have to find out. It is going to be I upon NEA. I is given 2 ampere. Number of charge particle per unit volume is given 2 10 to the power 8. The charge on a single electron is also given, and cross-section area is also given, right? So everything is given. Just put the values and you'll get the answer of VD, right? This is for you to do it. Now look into this question. The number density of the free electron in the copper is nearly this. So the charge per unit volume is 8 into the power 28 per meter cube, right? A copper wire has its area of cross section 2 into the power minus 6 meters square. So area of cross section 2 into the power minus 6 square meter square, and it is carrying a current of 3.2 ampere. It is carrying a current of 3.2 ampere. Right? What will be the drift speed of the electron? E, the value of E already know 1% per 19, right? 10 to the power minus 19. So the drift velocity speed of the electron, by the same method, you can just solve it and get the value of drift current. No problem with that, right? Now look into the current density. So the current density we have defined as a vector, and the direction of this vector is perpendicular to the cross-sectional area, right? So it is simple. Current density is simply current flowing through a unit cross-sectional area, right? Current density is current flowing through per unit cross-sectional area of a given conductor, right? Okay. Right, let's move on and talk about the next idea. Temperature dependence of resistance. For metals, it increases with increase in temperature, right? For semiconductors, so what is the meaning of that? Let me explain you within a separate page, right? Okay, so temperature dependence of resistance. You see that? So over here you see that R is R naught 1 plus alpha delta T, right? So you see that if the temperature difference is increased, so resistance of the wire will increase. But this is true for conductors. Understand in this way. The resistance of the wire is also written as rho L upon A. Alright. The value of rho, let's say the length of the wire and the area of cross section is not changed. Then the resistance only depends on rho. Right? And the factor, the rho depends on two things. Right? Rho depends on two things. Right? What is happening? The relaxation time, the resistivity of a material is inversely related to how many electrons are available, how many charged particles are available per unit volume. If the material has more charged particles in a unit volume, it's a good conductor, na? So the resistivity will be lesser, right? And if the conductor has higher relaxation time, means charged particles can move easily through it, right? So the resistivity will be less, right? Okay. Resistivity of the material tells that how difficult it is for the current to move through it, right? Okay. Now you see that when you increase the temperature, two things happen, right? When you increase the temperature, what will happen? This is a given conductor. In that conductor, there are a lot of atoms, right? And when you give energy, when you increase the temperature, you're giving the heat energy. Lot of electrons simply pop out of the atoms, and they are freely available to take the energy from one end to the other end. These become the free electrons, right? Okay. Now, my dear kids, we know that these free electrons are the responsible factor for carrying the current, electricity from one end to the other end. So increasing the temperature increases the number of these free electrons. That's a good thing, right? Increasing the temperature increases the number of free electrons, right? Increasing the number of free electrons means reducing the resistivity. That means reducing the resistance, right? Okay. So temperature is increasing the number of free electrons, and that is effectively reducing the resistivity and reducing the resistance. Good. Now, increasing the temperature also increases the random motion of the free electrons as well. So whatever free electrons we have, if you increase the temperature, they get the energy and they start moving randomly. Due to that random motion, they collide more, and if the collision are happening much frequently, the relaxation time, the time for which no collision was happening, is reduced, right? So increasing temperature means more collision and the relaxation time is reduced. Relaxation time is reduced. So if tau is reducing, so the rho will increase. So this will increase rho, and that will increase the resistance. You see that one effect of temperature is reducing the resistance, and other effect of temperature increase is increasing the resistance, right? So you see that increasing the temperature creates both the effects simultaneously. Increasing temperature wants to reduce the resistance and increase the resistance at the same time. It depends on the material which of these two factors is prevalent. If this factor is prevalent or more effective in the given material, so this factor will dominate and the resistance will reduce due to the increase in temperature. If the second factor is dominating, right, in a given material, then increasing the temperature will reduce the relaxation time and increase the resistance. For example, in the case of conductors, there are already a lot of free electrons. So increasing the temperature will increase the number of free electrons in the conductor, but that will not bring a significant change in the droppage of resistance. But there are a lot of free electrons in the conductor already. Increasing the temperature reduces the relaxation time by increasing the number of collisions, right? So in a conductor, when you increase the temperature, collisions happen much frequently. And when the collision happen much frequently, what happened? Collisions are happening much frequently, then what will happen? So this is happening much frequently, the relaxation time will reduce, and that will increase the resistance, right? So in the conductors, the second factor is more dominating, because the conductors already have a lot of free electrons. So this factor is overshadowed by the second one, and this is why the conductors show an increase in resistance when you increase the temperature, and this formula is applicable. On the other hand, when we talk about the semiconductors does not have that many free electrons. So this relaxation time, this factor is not that prevalent. The first factor is dominating, right? Here in the semiconductor, when you increase the temperature, the number of free electron increases, and that reduces the resistance. So semiconductor gets lower resistance when you increase the temperature. I believe the idea is very clear, right? Okay. So now you have it. A copper coil has a resistance of 20 ohm at 0 and has a resistance of 26 ohm at 80. Find the temperature coefficient of the resistance of copper. So very simple. R equals to R naught 1 plus alpha delta T. So the resistance of the wire at temperature T. A copper has a resistance of 20 ohm at 0 degrees Celsius. So the initially it was 20, right? 1 plus alpha. The value of alpha we have to find out. Temperature difference. From 0 to 80 we are going. So temperature difference is 80. Right. You don't have, whenever you are writing delta T, you don't have to convert centigrade to Kelvin, right? But when you are using the temperature only, then you have to use it in Kelvin in the entire physics, right? Okay. All right. R, right? So what is the value of resistance? Finally, we can say that the resistance finally become 26.4. So you see that there is only one variable, which is alpha. You just solve this equation, get the value of alpha. So this is for you to solve, right? Let's move on and talk about the next idea. Factors affecting resistance, we have just seen that, right? We have seen that the dominating factor will decide, right? There are two things that will happen when you increase the temperature, right? There are two factors affecting the resistance. I have just told you that resistance is rho L upon A, right? If you just don't change the geometry, by changing the geometry, we have seen it, right? If you increase the length n times, the resistance will become n square times, right? Provided the temperature and other things are not changed, right? But the other factor is, if you change the rho, and the factors on which the rho depends is, I have already told you, it depends on the relaxation time and the number of free electrons, right? So changing changing the temperature changes these things, and if it affects the value of resistance, right? Okay. Now the next thing is called as VI characteristics. VI characteristics is how the voltage and current varies through a given circuit element. Resistor is one circuit element that we can deal with a current circuit, right? But we can have different circuit components as well, right? When we talk about the VI characteristics, we are dealing with the relation between voltage and current through a given circuit element. When you attach a given resistor, let's say that this is a variable voltage supply, right? Variable power supply. So what is happening? We can change the applied voltage, right? So let us use this arrow over here. So I am showing that the value of voltage I can change at my well, okay? And there are two terminals, right? So this is across this terminal. I have used a resistance, right? So I found that across these terminals, when I use a resistor, when I increase the voltage, the current also increases, right? So such circuit where V and I are proportional, this is Ohm's law, right? These circuits, these elements, right, these conductors that follow the Ohm's law are called as ohmic conductors. These circuits are ohmic circuits, right? The conductors where V is proportional to I are ohmic conductors. And similarly, between these two terminals, I can also connect another element or another conductor which is not following the Ohm's law. That means if you double the voltage, the current is not doubling. Let's say if you double the voltage, current is also increasing by 10%. If you increase the voltage, let's say 10 times, current increases by 40%, like that. So you see that current is increasing, but not in proportionality, right? Or let's say that voltage is increased, but the current does not change at all, right? So all those conductors which do not follow the Ohm's law are non-ohmic conductors, right? So ohmic conductors will of course follow a proportionality between V and I, and non-ohmic conductor will show a variation from the proportionality in different ways, right? I believe the idea is very clear. Now let us talk about the next part, which is the combination of resistance, right? Okay. So what is the combination of resistance? There are two possibilities in which resistances can be joined. So the first is series combination, the next one is parallel combination. You know that. In the series combination, the resistances will be joined one after the other, right? So the current is flowing through this one. The net resistance will be simply summation of individual ones, right? Okay. So R equivalent is R1 plus R2 plus and so on, right? R equivalent is R1 plus R2 plus and so on, like this, right? Okay. And whenever we have this series resistance, what happens? The current is same across all of them, but the potential difference depends on the values of resistances, right? The potential drop is different across the different resistor, right? We can simply solve it out and get the value of potential drop like this. We will use these values very not so frequently, right? But yeah, it's a good practice to remember these values directly, because sometimes they ask you a very simple question and then these values come in very handy. So there are two resistances, right? R1, R2, potential difference across them is V1, V2, current flowing through them is I, right? Okay. So what will be the potential drop across the first one? What will be the V1? V1 will be R1 upon net resistance R1 plus R2 into the total voltage V. And similarly, V2 is going to be R2 upon R1 plus R2 into V. I believe the idea is very clear. When you are in parallel combination, again, in the parallel combination, the current will divide in the ratio of their resistances in proportion to their resistance, right? Current will divide in proportion to their resistance. So now the lower resistance will get more current and the higher resistance will get less current, right? So what will happen? In the case of parallel combination, the effective resistance will be simply this, right? So the potential drop is same, but the current is divided. So the net current is I1 plus I2, which is what we have done, right? So you see that this is the relation that we have over here. The equivalent resistance is related with the original resistance in this fashion, right? So R1, R2 was the original resistance. The net resistance instead of these two will be 1 upon R equivalent, 1 upon R1 plus 1 upon R2. So this is something that you might know from your common sense, right? And you see that the current is divided. So what will be the current in the first one? Current in the first one is going to be R2, the other resistance upon R1 plus R2 into I. and current in the second one is going to be R1 upon R1 plus R2 into I. So these are the two values, right? Again, you don't have to learn them by heart, but if you do that, many simple questions can be done and the time can be saved, right? Okay, so now let us start solving the circuits, right? Everything that you have learned so far can be done with the help of circuit solving as well, right? In the case of series and parallel combination I'm talking about, right? So let's talk about the circuit solving. Many people consider that this chapter is all about circuit solving. But whatever we have covered so far, many times you will find that in the previous year question, if you see, some questions are directly asked from the first part, which is the basic part. And many kids do the mistake of only solving circuits and overlooking the first part altogether, right? You have seen that the stretching problem was very unique, right? Very special, and it is asked many times. The current density, the I is NEAVD, problems on that concept are asked many times. Relaxation time is a very important concept as well. So all these concepts, the temperature dependence of resistance is a very important concept as well. So this chapter is not only about the circuit solving, but circuit solving is a very important aspect, and that is what we are going to do right now. Let's start understanding the second part, which is the circuit solving. So now let us start with the hero of the chapter, which is the circuit solving. Many people think that this chapter is only about this circuit solving. So there are different cases in which you'll be solving the circuits. I'll be telling you lots of tricks as well. And I have invested a reasonable amount of time to select good problems. I have already hand drawn all the images and all the problems that I'm going to tell you, right? So it took me a lot of time doing that, right? But I'm assuring you that if you follow all these examples and illustrations that I'm going to show you, NEET problems will become piece of cake. And not just NEET problems, even if you try a previous year JEE Mains problem, those kids who are preparing at a slightly higher level, they can also try that out, but not at this moment, I would suggest. But I'll tell you that this theory is going to be enough for all the circuit solving problems from your NEET perspective, right? So let's start right away, right, and follow every problem one by one. So have a look at that. This is the description of the whole thing. So here we have the circuit reduction. Now the basic kind of circuits can be solved by simply reducing them, right? Circuit reduction, right? This method I'll tell you. And after that, there will be some circuits that you cannot reduce directly. And for those special circuits, we have these tricks, right? We will talk about that. And then we have KCL and KVL, that is nodal analysis and loop method. So all of these things are there in the picture. You don't have to worry about anything is, I'm leaving anything. I won't be leaving anything at all, right? If there is anything that is relevant to NEET, plus 10-20%, I will tell you in this particular video. No need to worry about anything, right? So let's start right away with the circuit reduction method. My dear kids, they will be the easiest kind of circuits like these, where it is possible for you to identify which elements are in series and which elements are in parallel. My dear kids, if you can simply look at the circuit and identify that if there are some elements that are in series or some elements are in parallel, you can solve such circuits by the method of successive reduction. Look into the situation. Here, these two resistances are visibly in series. So we can remove these two resistances and reduce the circuit, right? Then after whatever net resistance we will place here, that will be in parallel with this one. We can further reduce the circuit. So successively we are reducing the circuit to a smaller circuit and eventually solving it, right? So let us start solving such circuit. But before we do that, there are a couple of things I need to tell you, right? So here you just need to know two things. In series, if I have multiple resistances, so you just add them up now, R1 plus R2 plus and so on. So if all the resistances are same, R, they are all added in series. Let's say n times resistances are added in series, R plus R plus R plus R. So it will become n times R. Yes or no? Right. So if equal resistances, if n equal resistances are connected in series, the net resistance becomes n times R. No problem with that. And if parallel resistances are in series, then what will happen? 1 upon R net is going to be, right, 1 upon R net is going to be 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on. If all resistances are same, 1 upon R plus 1 upon R plus 1 upon R plus 1 upon R, so it will become N upon R. So the net resistance will be just inverted, R by N, right? So this is something you can keep in mind. right? This is something which is more important. If n resistance are in series, net resistance will become n times r, all of them are same. And if n resistances are in parallel and all of them are same, then net resistance will be r by n. So if two resistances r and r, they are in parallel, then the net resistance will be r by n, r by 2. If three resistances are in parallel, right, and the net resistance, the combined resistance, the equivalent resistance of all three of them will be r by 3, right? Okay, the net resistance will be r by 3. I believe the idea is very, very clear. Okay, and now if two resistances which are not equal, they are connected in parallel, you can also remember this point as well. If two resistances are there which are, are not same and they are connected in parallel, so what will be the net resistance? We can say this will be that 1 upon r net resistance. So net resistance will become r1 r2 upon r1 plus r2, right? So if let's say 3 ohm and 6 ohm, they are connected in parallel, then the net resistance will be 3 into 6 upon 3 plus 6. So it is 3 into 6 is 18 and 3 plus 6 is 9. 18 upon 9 is 2 ohm. So net resistance will become 2 ohm, right? So I believe the idea is very, very clear. So these three things will become very handy while solving the circuits. So this I am telling you this, right? So while solving it, just keep those things in your mind, right? So here you have to solve it by successive reduction. I have told you already that if by simply looking at the circuit you can tell that some elements are in series and some elements are in parallel, then you can solve such circuits by method of successive reduction. So here R and R in series, right? So n resistors are in series, the net resistance will be n times R. So two resistors are in series, net resistance will be 2 times R, 2R. So you can replace them with the net resistance of 2R, okay? Then that resistance and this one will become in parallel. If R and R, two resistors are in parallel, the net resistance will be R by N. So 2R and 2R are in parallel, the net resistance will be 2R by 2, right? So 2R by 2 is R only. So you can remove these two resistances and between these 2 points, add just one resistance of R, right? So just let me draw it, right? So you have this R, right? And this will become 2R, 2R and 2R will become parallel, that they will become R. So let me just draw it. This is R, this is R, right? So here you have 2R, here you have 2R, let us quickly draw it. Then you have R and 2R again, so you have R and 2R again, right? You have R and R again, so you have R and R again, all right? And this is it, right? And this is it. I believe the idea is very, very clear. So you see that this is what we have done. Between these 2 points, we have replaced all three resistance with net resistance R, right? So you have successively reduced it, right? The remaining resistance are as it is. The remaining resistances are as it is. Okay. So now you further remove these two, right? With 2R. Okay. So just do that, right? Just further, you can reduce these two resistances. Okay. Reduce these two resistances. Okay. Remove them and add one resistance in place of that, which is 2R. So now you see this 2R and this 2R are in, this is also 2R, this 2R and this 2R in series, in parallel, sorry. So what will happen? We can remove them, R by N. So 2R and 2R is 2R by 2, which is going to be R only, right? Okay. So now you see that R and R again are in series, right? So you can replace them with one resistance, that is going to be 2R. All right. Now 2R and 2R again are in parallel. So the net resistance will be R by N. They 2R by 2, which is R only, right? So again R and R in series. So the net resistance will be 2R. Replace them with net resistance 2R, right? Now 2R and R, these two resistances are in parallel. The net resistance, they are not same. If R1 and R2, two resistances are there, and they are not same, so net resistance will be R1 R2 upon R1 plus R2, right? So R1 R2 upon R1 plus R2, this will be the net resistance between these 2 points. So it will be 2R by 3, yes or no? 2 by 3R, this is going to be the net value. This is going to be the net value. I believe the idea is very, very clear, right? And if there is any question or confusion, you can definitely ask me, right? That's how you can solve it. You had elements, and consecutively you could find out which elements are in series and which elements are in parallel. You can visibly see it, and successively you have reduced the circuit into a much smaller circuit and you have solved it without any problem, right? Have a look into this circuit as well. Look into this circuit as well. Right now what is happening? You can again identify that you have to find the net resistance again here. Right, here you can again see that two elements are in parallel with one another, right? If two resistors are not same and they are in parallel, so the net resistance of those two will be R1 R2 upon R1 plus R2, 3 into 6 upon 3 plus 6, so 18 by 9, 18 by 9, 3 into 6 upon 3 plus 6, 18 by 9, which is 2 ohm. So the net resistance of these two will be 2 ohm, right? So you see that remembering basic formulas, it increases your speed. So you see that 4 and 2, remove these two with a single resistance, right? So 4 and 2 will become in series. So series, that means this will become 6 ohm only, right? Okay. So now 6 ohm and 3 ohm are in parallel. So 6 into 3 upon 6 plus 3. So what will be the net resistance? 6 into 3 upon 6 plus 3, 18 upon 9, which is going to be 2 ohm. So again, this whole thing will become 2 ohm. All right. So you see that this 2 ohm and this 6 ohm are in series. So again, this 2 and this 4, again they will reduce to 6 ohm, right? Again, they are in series. All right. So you see that this is the point. You have 6 ohm, right? And then there is one arm or one more arm, that is 3 ohm. All right. So 3 and 6 are in parallel to each other. So 3 into 6 upon 3 plus 6, which is 2 ohm. So the net resistance of this thing is going to be 2 ohm only, right? So I believe the idea is very, very clear, right? If there is any question or confusion, you can definitely ask me, right? Let's move on and talk about the next idea. Now, so far we have seen a very simple kind of circuit where we have clear understanding that these elements are looking into series, right? We can see that these elements are in series. We can see that, we can tell that these elements are in parallel. We have successfully reduced the circuit into a much smaller circuit and solved it, right? These are basic problems, you can say. But right now, there are many cases when you cannot identify it very easily that some elements are in series or some elements are in parallel. So in such circuits where you cannot identify that which elements are in series and which elements are in parallel, you need to, apply your brain and you have to observe much deeply, right? And try to apply some special tricks, right? So you see that if one of these three things, if you can identify one of these three things, then you can go with these three things, right? These three tricks, right? Otherwise, you have to go with the KCL or KVL method, right? So that I'll tell you after that. But look into these things, right? Circuit with connecting wires. So these things will happen, short circuit and equipotential points. Let's have a look at the first thing, and then we will consecutively look for the symmetric circuit and ladder circuits. So let's first have a look at this thing, right? So we are going to see a circuit where identifying which elements are series and which elements are in parallel is not going to be easy, right? We cannot directly tell that, and we have to find the net resistance. How can I do that? Okay, let's have a look at that. So the basic concept is this: if I have a current flowing in this direction and there is a resistance in the path of the current, so what will happen? This resistance will create a drop in the potential of the flowing current. You see that the current is flowing like this. So when the current is going to pass through the resistance, what will happen? If the resistance is R, the potential drop across the resistance will be IR, right? All right. So if the resistance is dropped, the potential drop that it is going to cause is also drop, right? Okay. So the potential drop will also reduce. So if the resistance is 0, the potential drop caused by the resistance will also become 0. Yes or no? If the resistance is 0, the potential drop caused by the resistance will also become 0. Yes or no? Okay. If the resistance is 0, then the potential drop caused by the resistance will also be 0. Okay. If the resistance is 0, that means it is simply a connecting wire, right? Okay. If two points are simply joined, there will be no potential drop across them. Basically, we can say that they are the exact same points. They are the equipotential points, right? So have a look at that. These are the 2 points. There is no resistance between them. There will be no drop of potential between them, right? So the point number 1 and point number 2 will share the same potential, which is why point 1 and point 2 will become equipotential point. What do you call it? Equipotential point, right, equipotential points. And since they are equipotential points, so while solving the circuits, we can consider them as one single point only. So we can remove this wire and we can call point 1 and point 2 are same. Have a look into this situation, right? So this is the application of the concept. Have a look into this. We have to find the net resistance between the terminal A and terminal B in this situation, right? How to do that? With the application just we have just learned, we can do that very easily, right? Now we don't have to solve these kind of problems directly. We can tell the net resistance is going to be something, right? So you will just tell that, right, in simply by looking at it. Let me explain first, and you just don't need to solve it, but let me tell you just to explain the concept so that we can solve a better problem. I have those problems as well. So here it is. Look into these 2 points. These points are connected with a connecting wire, right? So simply by observing the numerical, I can say that these 2 points are connected with a connecting wire, point number 1 and point number 2. So there will be no potential drop between point number 1 and point number 2. If there is no potential drop between point 1 and point 2, so these are the same points. Basically, I can join them, right? So point 1 and point 2 are same. All right. So between point 1 and 2, these 2 resistances are there. All right. These 2 resistances are there, and this is 1 and A, and this resistance is there between 2 and B, right? All right. So now you see that the current that enters A will follow this path and go towards B. Current is moving like this, right? Current that enters A will move towards B like this. Now think about it. This entire path, this entire element is simply hanging off this point, and it is not a part of the closed circuit. Yes or no? This entire thing is not a part of the closed circuit, and we may drop it. Yes or no? We may drop it. This is not going to get any current. Current will simply flow like this. Yes or no? Because this thing is not a part of the closed circuit, right? It is simply hanging off this particular point. Okay. Now, since this is not contributing to a closed circuit, it will not get any current. So the remaining circuit only has this R and R. The net resistance will be 2R. That's it. And now we have just simply looked at this situation, and without solving it, we could have told the same thing, right? We could have told that these 2 points are same. So we can say that these 2 points are at the same potential. So this will become redundant, and the remaining resistance will be 2R, right? So without solving, you can solve these things. But anyway, right, so net resistance here is going to 2R. Just apply those concepts over here. This is a very good kind of problem. These kind of problems have been asked in the previous year as well. So have a look into this situation. Here we have 2 connecting wires like this, and we have to find the net resistance between A and B, right? Okay, have a look into this situation. Let's take a different color this time. So here we have A, right? Here we have A, right? And see what is happening in this situation, right? Here we have A, right? This point and this point, they are connected directly, right? Look into this situation. This and this. This whole thing is connected with a connecting wire to this point. So this is also point A, this is also point A. They are all point A. The potential of if A at A is VA, here also you have VA, and here also you have VA, right? Similarly, this point is B, the potential here is VB. Over here also it is going to be VB because they are connected with a connecting wire, right? So now if you draw the point, this is VA, this is VA, this is VA, right? So if you draw the points, point A and point B, at point A the potential is VA, at point B the potential is VB. Between VA and VB we have this 3 ohm. Between VA and VB we have 6 ohm. And between VA and VB we have 2 ohm. Alright. Since all 3 resistors are in parallel, the net resistance is going to be simply 1 upon R is going to be 1 upon net resistance is going to be 1 upon 6 plus 1 upon 3 plus 1 upon 2. So you 1 by 6 plus 2 by 6 plus 3 by 6. So 3, 2, 5 and 6, 6 by 6. Right. So I believe the idea is very, very clear. Just take the LCM and solve it. You will have the final answer. I believe there is no particular problem in this particular question. Net resistance is going to be 1 ohm only. Right. So that's it. Right. So join it. 1 by 6 plus 1 by 3 is just simply 2 by 6, and then you have 3 by 6. right? 1 by 2 is 3 by 6. So 3 to 5 and 6, 6 by 6, that is 1. So net resistance is going to be 1 ohm over here, right? So this is simply, you can solve it. This is how you can simply solve it, right? Have a look into this situation as well. Again, another problem. Here we have a connecting wire that is showing that it is not connected over here. It is jumping across this point and connecting to this point, and this is also a connecting wire, right? So again, a connecting wire problem, and let us try to solve this one as well, right? So without any further delay, we can solve it. Like here we can say that, let's say there are some points over here. Let's call it point number 1, right? Let's call this point as point number 1, and here you see that there is no resistance in the path, right? So we can say that this will also become point number 1, right? No problem with that. Let's call this point number 2. Here we have no resistance in the path, so this is also point number 2. No problem with that, right? Now, between point number 1 and this point, we have one resistance. So let's call this point as different 3, right? And let's similarly, between 2 and this point, we have another thing. So let's call it point number 4, right? I believe there is no problem in this particular part, right? Okay. Now what is happening? Let's try and solve this particular idea, right? You will see that between point number 1 and between point number 1 and point number 4 are same, right? Point number 1 and 4 are same, and point number 2 and 3 are also same. Yes or no? Simple. So we can solve it like this, right? We can solve it like this. We can make point number 1, 4 over here, and we can keep 2, 3 over there. All right. So between 1 and 3, we have this resistance R. Between 1 and 3, we have one resistance R, right? And between 2 and 4, we have another resistance R. Between 2 and 4, we have another resistance R, right? That's it. So 1 is A and 2 is B. All right. So between A and B, we have two resistance R and R. The net resistance will be R by 2. I believe the idea is very, very clear. Now let us start solving another question on the same concept. We have, you see that this kind of circuit, and we have to find the net resistance between these two terminals A and B, right? Very easy. Let's call it this. This is the point number 1. This is the point number 2. There is no resistance between these 2 points. This is also point number 1. This is also point number 2, right? Because there is no resistance here as well. So now if you look further, you see that between this point and this point, we have a resistance. So we cannot call these 2 points the same potential. We have to call this another point, let's say 3. And again, between 2 and this point, we have another resistance. So let's call it 3 and 4. Look into point 3 and point 4. These two, there is no resistance between them. So point 3 and point 4 are basically the same points. So here you have point 3 and point 4. Point 1 and point 2 are separate. So point 1 you can draw over here, and point 2 you can make over here, right? So see that between 1 and 3 you have this resistance. Let's cover all the resistance. Between 1 and 3 you have one resistance. So this resistance is taken care of. Between 1 and 4 you have another resistance, right? This one. So let us, between 1 and 4, between 1 and 4. So this is 1 and 4. Another resistance R. Between 1 and 2 you have another resistance R. This one. Between 1 and 2 over here like this. Okay. All right. So these three are taken care of. Between 3 and 2 another resistance R is there. They are not connected. You see that it is jumped over. Between 2 and 3 this is another resistance R. 2 and 3 another resistance R, right? This is also taken care of, right? And at last, between 2 and 4 another resistance R is there. Between 2 and 4 another resistance R is there, like this, right? So now this circuit is very, very easy to understand and very easy to solve. We can directly solve it. R and R are connected in parallel, so net resistance of them will be R by 2. R and R are connected in parallel, net resistance will be R by 2. Then these two are in series, the net resistance will be R by 2 plus R by 2, that is R, these two and this two. This will become R by 2 plus R by 2, the net resistance will be R. So R and R, they are in parallel now, so the net resistance will be R by 2. So this is going to be the final value right over here. So I believe there is no confusion in this particular part. Let's have a look into this another question, right? This is another application of this concept, right? Have a look into this question and try to solve this one as well. So here you have this kind of situation going on. Let's call it point number 1. Let's call this point is point number 2, right? Let's name point number 3, point number 4, point number 5, point number 5, point number 6, like this, okay? Now just focus, between 1 and 3 there is no resistance, between 3 and 4 there is no resistance, right? So point number 1, 3 and 4, they are basically the same points, right? Point number 1, 3 and 4, they are basically the same points. You can draw them at one place. Point number 6 is there, right? But point number 5 and 6 are another same points, right? Between you can say that point number 5 and 6 there is no resistance between them, so they are equipotential points. 5 and 6 are at the same point. Now you have already drawn 1, 3, 4 and 5 and 6, and only point number 2 is remaining. So point number 2 you can make over here, no problem with this, right? Okay. Now you just draw all the resistances one by one. Between 1 and 6 you have one resistance R, right? Between 1 and 6 you have one resistance R, all right? Between 3 and 6 another resistance R, 3 and 6 another resistance R, all right? This one is also taken care of. Between 3 and 5 another resistance R, between 3 and 5 another resistance R, all right? This is also taken care of. Between 4 and 6 another resistance R, between 4 and 6 another resistance R, all right? This is also taken care of. Between 4 and 5 another resistance R, between 4 and 5 another resistance R, all right? So all resistances are taken care of, right? Just one is remaining. It is between 2 and 6. It is between 2 and 6. So just make the point number 2 over there, right? Point number 2 over here. Between 2 and 6 we have this resistance, all right? All right, so solving this will be very, very easy. 1, 2, 3, 4 and 5 resistances are in parallel with each other, and all of them are same. The net resistance will be R by N. So between these 2 points, the net resistance will be R by 5, right? And then we have another resistance R, right? Now you can see that these 2 elements are connected in series with each other, right? So the net resistance will be simply the summation of this thing, R by 5 and R. So it is 5R by 5 and R by 5. It is 6R by 5. This is going to be the net resistance of this entire circuit. I hope we have understood how to solve any particular circuit that looks like this and that has connecting elements like this, right? Simply we can understood this particular concept that if 2 points are connected with a connecting wire, then those 2 points have to be they are equipotential point, and we can draw them at one place, right? And we can then redraw all the available resistances and simplify the circuit. Then we solving the circuit is very, very easy. So whenever you look at the circuit that you have to solve, if you can identify the connecting elements or normal wires into it, you can simply remove them with one single point, right? So that's it. Let's move on and talk about the next idea and talk about the next point, which is method of symmetry, symmetric circuits. Very important and very easy to solve. Let's have a look at that. So far what we have seen, my dear kids, that we have some circuit and we are trying to solve it, whether we are solving it by successive reduction or we can just find the equipotential point with the help of a connecting wire, right? So that we can identify those 2 points as one and solve it further, right? Now, while solving the connecting wire problems, we have understood that if we somehow figure out some points are equipotential, we can combine all those points as one, and then solving the circuits becomes much more easier. That means having equipotential points in the circuit, or the points which are at the same potential at the circuit, makes the circuit solving very, very easy, right? Now what we are trying to do right now, we are going to use a symmetry that is visible in the circuits, that is visible in the given circuits, to solve the circuits in a much easier and much fun way, right? Symmetry of the circuit sometimes exposes that there are some equipotential points available in the circuit, right? And by doing so, by having a look at those points, we can further reduce that particular circuit in a much simpler, much easier circuit to solve, right? Let's have a look at that, how to do it, okay? So here we have 2 possibilities, parallel axis of symmetry and perpendicular axis of symmetry, right? With these two axes of symmetries, we can find the equipotential points and reduce the circuits in much easier ways. Have a look into this situation. Now, right now, look into this circuit, right? Look into this circuit. This is the first possibility where we have a parallel axis of symmetry. What is that? Yeah, this is the point A, and this is the point B. Right, the current is entering over here and the current is leaving the circuit over here, right? So current is moving like this, right? Current is, it starts like this and it spreads out and then it comes out like this, right? Okay, so this is the direction of current. Okay, now along this axis, look above and look below. Can you fold this entire thing and everything overlaps on one another or not? If that happens, which is happening right over here, right? If you just take this circuit, right? This is the axis along which the current wants to flow, right? And if you flip the entire thing, right? If you flip it about this axis, the every resistor below is going to overlap every resistance above, right? That means there is an axis of symmetry that lies along this axis. This axis is called as parallel axis of symmetry, right? If you find parallel axis of symmetry, then what happens? All the points that are across the axis of symmetry, for example, these 2 points are, this is how the current starts to flow from this end to this end to this end. This is your parallel axis of symmetry. Now, there are any points that are across the parallel axis of symmetry, all those points will be at the same potential. So what will happen? Here, look into this point and this point, they are across. This is the axis of symmetry and these 2 points are across the axis of symmetry. So this and this point will be at the same potential. Now, since these 2 points are at the same potential, what will happen with this wire? Will this wire carry any current? We can say no, this wire will not carry any current and we may reduce it, we may drop it, all right. So this is what going to happen, right? So we can remove any element that is connecting between these 2 points, right? This on this, on this axis which is perpendicular to the parallel axis of symmetry, right? Okay. So this, all the elements perpendicular to this parallel axis of symmetry become, redundant. So we can remove it and the remaining circuit will become like this. R, right? And something like this, R, right? And then you have another R, all right? And R, all right? Okay. So now what will happen? Now you can see that all 3 elements, you can simply add them in parallel, right? So what will happen? This element and this element are in parallel, this element and this element are in parallel and things like that. So this and this are in parallel, this and this are in parallel and you can further solve it, right? So you can further say that this and this are in parallel. This is the circuit that you have. These are the 2 resistances in the middle. This and this will become in parallel, right? And this will become in parallel. All right. Now you can solve it. R and R are in parallel. Here R and R are in parallel. So R by 2, they become in series. So this will become R. Again, you can solve it the remaining circuit. So this is how you can go about it. Let's have a look at some problems and try to solve it. Right. So this is the parallel axis of symmetry. This is the line across the parallel axis. These all points are going to be at the same potential and there will be no current flowing across it. So those elements can be removed from the circuit and circuit can be simplified, right? This is another axis of symmetry as well. Observe this as well and then we will solve the problems on it. So here it is, right? Here it is. So right now you will observe that if this is the axis about which if you try to fold it, you can easily fold that, right? And the whole thing will overlap one over the other, but you do not find the points over here, right? So this can confuse you. But if you observe this one, if you take this line and try to fold it like this, you can also find one axis of symmetry like this. The current wants to move from here to this place, but if you take this axis, this is the axis perpendicular to the axis along which the current is flowing. So this is a perpendicular axis of symmetry because about this one also the flow, the same overlap will happen. Now in this situation, what happens generally, that the current that is flowing from one end, it will move like this, and the current that is moving this way, right, it is going to move like this, right? So what will happen? At this junction, the current does not divide. And if at this junction, the current is not dividing, so basically we can detach the wire at this junction and make our circuit easy, right? So whenever we find the perpendicular axis of symmetry, so what will happen? The junction that is forming at the center, we can detach the wire at the junction and we can simplify the circuit like this. So what will happen? So this resistance is there, this resistance is there, this is R, right? So this is R and this is R, all right, like this. This is R, all right, this is R, things like this. This is R, all right. So we have just detached it and now the remaining wire circuit can be drawn as well. R, this is R, and then finally this is R, all right. You see that by detaching it, the whole thing becomes very simple, right? These two are in series and then it will become in parallel with the third one. These two are in series, it will become parallel with the third one, and you can further solve it by successive reduction, right? So this is how we can go about it. So at perpendicular axis of symmetry, we can use it to detach the resistor branches falling on it. So if you have this perpendicular axis of symmetry, so resistor branches which are falling on it can be detached because the current does not divide at those places, right? So yeah, let's solve it. Let's solve some problems on this particular concept, right? Let's solve some problems on this concept. Over here, look at this particular problem. If you try to solve it by successive reduction, you can identify which elements are in series and which elements are in parallel. Can you identify it? By looking into this circuit, if you have to find out the net resistance, right? So let's say that we have to find the net resistance between A and D. This is the question. We have to find the net resistance between A and D. This is what we have to find out, right? Now, by looking into this circuit, tell me, is it possible for you to find out which elements are in series and which are in parallel? We can say no. Directly we cannot tell that. But can you find out there is some axis of symmetry? Think about it. So between A and D, you have to find that this particular thing. So these are the points of interest. Think about an axis passing through this point, right? If I imagine an axis passing through this point, you see that I can overlap anything that is on the right side to the left side, right? Okay, so the whole thing is overlapping one on the other. Now, if I have this axis of symmetry going on, right, this is how the current wants to flow. It will enter at A and it will leave at D, right? This is how the circuit is, right? These are the two terminals. Now think about it. If I have this axis of symmetry, then any points that are across, if the current is flowing in this way between A and D, so any points that are across, any terminals that are across this A and D, across this axis of symmetry, they will be at the same potential and they will be at the same potential. So what will happen? These two axes, look into these points. We can say these 2 points are across the axis of symmetry, right? Across the axis of symmetry. So E and F will be at the same potential. Similarly, this particular arm, this is also perpendicular to this axis of symmetry, so they will all B and C will also be at the same potential, right? So we can say that these points are equipotential points, right? And similarly for these 2 points, point B and C are also equipotential points. So we can remove these wires that are connected over here. And now if I remove the wire, the circuit will become much more easier, right? If I say that these points are equipotential, these 2 points are equipotential points, these 2 points are equipotential points, right? So I can remove these resistors in between, and if I remove it, the circuit will become like this, right? And now solving it much easier. So we can say that now about this one, I can overlap. So this one, and if you just overlap it, 1 and 4, this one, resistor number 1 and 4, they will overlap on one another. So they will become parallel to each other. 1 and 4 are overlapping. 2 and 5 are overlapping on one another. So 2 and 5 are also in parallel, right? Similarly, 3 and 6 are going to overlap. So 3 and 6 are also in parallel. So this is the new circuit, right? Solve it. R1 are in parallel. So R1 by 2, R1 in parallel, R1 by 2, and R2 in parallel, R2 by 2. So this is going to be the next case, right? So this is the next circuit, and you can further solve it. So simply by observing one thing and one thing only, that is simply by looking for the axis of symmetry, you have solved this kind of circuit very, very easily, right? Have a look into the another problem, right? Look into this question. In this one, what is happening? We have to find out something, right? What we have to find out in this particular question, we have to find out the net resistance between A and B, right? We have to find out what will be the net resistance between A and B, right? So very easily we can do that. Okay, very easily we can do that. Now think about it. If I just imagine an axis passing through between A and B, I can easily, find that everything above the axis is overlapping with everything below the axis. So these two things are overlapping. So there is clearly an axis of symmetry over here, right? There is clearly an axis of symmetry over here. Very nice, right? So if this is overlapping, okay, right? If this is overlapping with this, now, but look into this axis, right? We can say that these are the points across the axis of symmetry. This is parallel axis of symmetry, and these are the points across. So we can say that this arm can be, every element of this arm can be removed. So this arm, every element of this arm is removed. Then what will happen? Every element of this arm is removed. So the remaining circuit will be much easier, and all other elements will become parallel. This will become in parallel combination with this. This will come in parallel combination with this. So let us directly draw it. So this is how the remaining circuit will be. All right. This is R, this is R, this is R, this is R. All right. So this is R. This is R. I believe the idea is very, very clear. This R and this R, this R and this R. All right. And this can be removed. Okay. So it will become R by 2. R by 2, they are in series. So the net resistance will become R. R and 2R are in parallel. You can further solve it without any problem. Right. So here, this one, and this one. So here you have R by 2. Here you have R by 2. And here you have 2R. R by 2 and R by 2 will further join up in series and will become R. So here R, and then you have 2R, and they are added across this one. So R into 2R upon R plus 2R going to be the net value, right? R into 2R upon R plus 2R is going to be the net value. So yeah, now have a look into this particular concept, which is concept application 3. Here if you just observe, we do not have this particular axis of symmetry because we cannot find any point that is across and remove the resistances. We have this axis of symmetry, but if I take the point across, I cannot remove anything across it, right? Because there are no resistance that are falling on this line, right? So taking this axis of symmetry is not useful for me. But what about this axis of symmetry? We also have this axis of symmetry as well, perpendicular axis of symmetry, right? And we know that whenever we have this situation going on, what will happen? At this particular point where the resistors are joining, the current does not divide at all. And since the currents are not dividing, whatever current is following this path, it goes like this, and whatever current is following this path goes like this. So we can detach the wires, right? So if we detach the wires, it will become like this. If I just redraw the circuit by detaching the wire. So this is one resistance, this is another resistance, right? This is A and this is B, okay? And here we have another R, okay? Here we have another R, and then when we have one more R, all right? And then you have 2R and R over here, like this, right? No problem with this. And the same things are happening below the circuit as well. So here we have it R, 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 all right, and then 2 R's. Now, just think about it. R and R, they are in series with each other. So they will become 2R, right? So I can remove them over here. And instead of them, we can use a single resistor of resistance 2R, right? Okay. Now, R and 2R, they are in parallel. The net resistance will be R into 2R upon R plus 2R. So which is 2 by 3R. All right. So I can remove these two and I can introduce a single resistance of 2 by 3R. Okay. So I can remove these two and I can introduce a single resistance of 2 by 3R. Okay. Same situation I can do with this one as well. I can remove all three of them and I can introduce a single resistance of 2 by 3R. So I'll do that. 2 by 3R. right? Now what will happen? These three elements are in series and these three elements are in series. So no problem at all. I can simplify it. So this is R and this is R. In place of these two, I can simply write down a single resistance of 2R. This is R, this is 2R by 3, this is 2R, right? So in place of them, I can write down a single resistance of R and R are 2R, 2R and 2 by 3R, 2R and 2 by 3R. So that is 6 by 3 and this is 2 by 3. It is 8 by 3R, right? So 8 by 3R, this all three resistances will become 8 by 3R and same things are happening below as well. So it will become 8 by 3 as well. All right. So now all I have is these three resistances are in parallel with one another. I can simplify it. 1 upon R net is 1 upon R1, which is 8 by 3R plus 1 upon R2, which is 1 upon 2R plus 1 upon R3, right? Just solve it and you'll get the value of net resistance in this situation. I believe the idea is very, very clear. Now, let us move on and talk about the next problem, which is the ladder circuits. So how will you solve the ladder circuits? Now, if I tell you that this is an infinite ladder series and I have to find out what will be the net resistance of this infinite ladder series, right? Now, if I have to tell you that I have infinite ladder circuits and the resistance of this infinite series is X, right? The resistance of this infinite ladder is X. There are infinite such repetitions going on, right? Now, if I remove just 1, 2 or 10 resistances out of it, so because it is infinity, if I remove 1, 2 or 10 resistances out of it and take the resistance of the remaining part, it is still going to be X, right? Removing 1 or 2 resistance minus out of infinity will not affect the overall resistance, right? So solving these kind of ladder circuits involves that approach only, right? Just leave one one repeating arm and then apart from one repeating arm, take all the other arm as a common resistance X. You see that? R, this is repeating itself. So just take one arm that is repeating and take all other arm and say that the resistance of this whole thing is X. Since the resistance of whole infinite arm is X, you have assumed that. So we can say that the overall resistance of this thing can be assumed as X only, right? Understand one more time. Since since the whole thing is infinite ladder, right? We have to find the resistance of this infinite ladder. And we have assumed that the resistance of infinite ladder is X. So even if I remove one little portion out of it, the resistance of this remaining thing is still X. It will not change, okay? Now, I can now I have a circuit that I can reduce to something that I can comprehend. This infinite circuit is something we cannot comprehend, but we can now convert into a finite circuit, and this finite circuit we can comprehend. This is one unit that we kept safe for us, and all other circuit has a resistance X. So all other circuit, just put it as it is, right? Now you have this circuit that was infinite circuit. This is now a finite one. You can solve it and get the value of X from this one, right? What will be the net value of resistance? You see that R and X, they are in parallel with each other. So the net resistance of this is going to be R into X upon R plus X, right? Plus this one is going to be series in the combination of these two. So just add them up. This is going to be the net resistance of this whole thing, because this whole thing is representing the resistance of this entire thing, right? So we can say that resistance of this entire chain is X, right? We have just removed a little portion out of it that will not affect the overall resistance of this thing that we have assumed to be X only. So the resistance of this whole thing is X only. Now you can solve it and get the value of X, that is going to give you the net value of resistance, right? So this is a very methodological, method based problem, right? Where you have to convert an infinite circuit into a finite one that you can comprehend and solve, right? Get the value of X, and that is your answer. Now, having said that, now we can talk about the remaining two important heroes of this particular chapter, that is KCL and KVL. So without any further delay, let us solve the values of, let us solve it and understand what is KCL and what is KVL. So let's have a look at that, right? So KCL is, this is the first thing, KCL. It is based on law of conservation of charge. It says that at any place, charge can neither be created nor it can be destroyed. it is simply transferred from one body to another, right? Okay. Now, when we talk about KCL, there is one word that will come across us many times, that is called as node. So what is node? At node or junction, anywhere in the circuit where the current can divide, that will become node, right? For example, the wire is moving like this, and here you have resistance. So there is no node over here, but at this place, what is happening? One resistance goes this way, the other goes this way. So there is a possibility of current dividing into the two paths over here. So this point A is serving as a junction or a node in this particular circuit. Okay. Now, KCL is saying that at any junction, whatever current is entering the junction, same amount of current has to leave the junction. No current can stay at the junction at the node, right? So we cannot deposit the charge at any particular place, right? So this is what we are talking about. We can say current and exiting is same as current entering the junction, right? One way of saying this thing is that total current that enters or leaves at the junction, the summation of all the current has to be 0. We'll be using this format always, right? This is going to be very helpful for us and will make things easy for us, right? So total current at any junction, that is summation of current entering and leaving the junction, is going to be 0, right? Now, if you are representing current entering with a positive sign, by default you can represent the current leaving the junction with a negative sign. Current is not a vector quantity, but it is just a sign convention that will help us solve better and better problems, right? I believe the idea is very, very clear. Now let us talk about this idea. So here you have it. This is the junction or node. What is happening? I1, I2, I3. These are the currents that are entering the junction. And look into this, I5 and I4. These are the currents leaving the junction. So you see that current entering the junction and current leaving the junction, these summation of this and this is going to be same, right? So yeah. All right. Now the next thing is nodal analysis. So what is nodal analysis? Right. With the help of KCL, you can also do the nodal analysis, right? The fundamental idea behind the nodal analysis is, we'll be mostly using this analysis only, right? It makes things so much easier for us, right? So the fundamental idea behind this particular idea is summation of all the current at a node is always 0. Okay. Summation of all the current at a particular place is always 0. Now understand that. To apply a nodal analysis at any place, let's say that we have this resistance like this. Let's call this resistance as R1, right? This is point A, and beyond point A, we have this thing going on and this thing going on, let's say, right? This is R2 and this is R3, right? This is what we are getting right now, right? So this is point A, let's say, this is point B, and this is point C. This point A we had already assumed. So at junction, let's call this point as point O. Okay. Let's add this point is at junction. Let's call this point as point O, right? So for the sake of simplicity, always assume that the potential is highest at the junction, right? If we are assuming it wrong, let's say the potential was lower at this place and the current was moving higher to lower this way, we will get the value as with a negative sign. The current value will come out with a negative sign. That means the value that we assumed was incorrect. But for now, while writing the equation, always assume that junction has highest potential, and then you can write down the equation, right? So without any further delay, if you want to write down, let's say the current is entering this way, right? And it goes like this, and then it goes like this. Somehow something like that is happening, right? So you can simply say that at that particular point, at point O, what is happening? The net current is 0. So current entering is same as the current leaving, right? So over here, what is happening? VO minus VA upon R1, right? This is the current entering the junction, right? And now, or you can simply write, because the direction of current you have already established in this particular case, because the current you have assumed is in this direction, so it is higher to lower. So you can say VA minus VO upon R1 plus, you can say current is moving like this, higher to lower. So VO minus VB upon R3 plus, we can say current is moving like this, so higher to lower, VO minus VC upon R2. The summation of all of them is going to be 0. Now this serves as a very good value, right? Because the current direction we have already assumed. So we don't have to assume that this is a higher potential, this is a lower potential, because current flows from higher to lower potential. That's why we said directly we can apply this thing, right? So at any junction, we can simply apply it and simply we can solve it. So whatever values are given, we'll put it. Whatever thing we have to figure out, we will find it, right? Okay, let's have a look at a problem and then we will have better understanding of this thing. So here we have a simple circuit. This point is grounded. That means the potential of this particular point is 0, right? We have to talk about when the switch is connected, how much current will flow through this particular part, right? How much current is going to flow through this particular section, right? So this is 20 volt, this is 2, this is 4, this is 5, right? This is the junction we are talking about. Let's call this point is point O, and the current flowing through this part is X, right? Okay. So we don't know the potential at point O, first of all, right? We don't have any idea about the potential at point O, right? So we can easily get the value of potential at point O without any problem at all, right? Okay. The potential, okay, let's do this way. Let's say this, the potential at this particular point is X. Potential, this is the point O. The potential at point O is X volt, right? No problem with this part, right? So let's try and apply the KCL at this place, right? Let's do the nodal analysis at O. So we can say the current entering is going to be same as current leaving, or summation of all the current is going to be 0. So right now we have not assuming the direction of current. So without being very carelessly, we can just do that x minus 20 upon 2, x minus 20 upon 2 plus, right, x minus 0 upon 2, right, and then x, because direction of current we are going to assume anyway, right? So direction of current, if comes out to be with a negative sign, that means if any value comes out with negative sign, means the direction that we had assumed was incorrect, and the actual direction is opposite to that. So be very easy going with that and just write down the equation, right? So here we have what will be the value of current in this part. We can say x minus 5 upon 4, potential difference upon resistance, right? Summation of that is going to be 0, right? Now just solve it and you'll get the value of x first of all. So you have 2x minus 40 plus 2x plus x minus 5, that is going to be 0, right? So 2x, x is going to be 5x, 40 and 5 is going to be 45. All right, so x is going to be 9. I believe the idea is very, very clear, right? The x is going to be 9 volt, right? Now, after knowing the value of x, after knowing the value of potential at this place, 9 volt, and the other point is at 0 volt, the resistance of this arm is 2. How much current is going to flow through it? So it is potential difference 9 minus 0 upon the resistance, which is 4.5 ampere. So I believe the idea is very, very clear. It's a simple problem of nodal analysis that you can solve very easily based on that, right? So let us move on and talk about one more problem on this thing, right? Here you have it, and try to solve. Here you have it. Try to solve this problem as well. So what you need to do is, you need to find out the current through this 4 ampere arm, 4 volt arm, right? 4 ohm arm, like this one. Let's try to find out the current through this this arm, right? Try to find out the current through this one. Okay, this is what we are trying to find out. Okay, how much current will flow through this arm, right? Now again, we have the current distribution that will take place, and we have to find out the current through any particular arm. Very easily we can do that, right? Very easily we can do that. How can we do that? So let's say the potential at this particular point is x again, right? So try and apply the KCL over here. So we have x minus 15 upon 12 plus x minus 3 upon 4, x minus 3 upon 4 plus x minus 2 upon 6 plus x minus 4 upon 8. Summation of this whole thing is going to be 0, right? So just solve it and get the value of x first, right? So just solving it and you will get the value of x first, right? And whatever value of x you have, let's say you get 10 volts, right? So 10 volts, and here you have 3 volts. So 10 minus 3 upon, 10 minus 3, whatever that value gives you, 10 minus 3 is 7 upon 4 volt. That is the value of current through this one, right? Very easily you can get the value of current through any particular arm. Let's say you want to get the value of current through this arm. You get x minus 4, that is 10 volt minus 4 volt upon 8. So 6 by 8 ampere. So just get the value of x and you can get the value of current after that. Alright, so let us start talking about the next idea, which is Kirchhoff's voltage law now. So what is Kirchhoff's voltage law? Just as KCL was based on law of conservation of charges, KVL is based on law of conservation of energy, we can say, right? So understand in this way. Here it is a tall building, for example, and you take a ball to the top of the building. What will happen is potential energy will rise because of all the work that you have done. And if the ball come back to the same place, right, what will happen? Because it is coming back to the same place, the change in potential energy after it came back to the same place is 0, right? As long as it was higher, the potential energy was higher. Now it came back to the same place, the potential energy again is at the same level it was before, right? So the change in potential energy is 0, right? Now the same thing is happening in a circuit. What happens? This energy is provided by the battery and all, right? So what will happen in a circuit? If you analyze a circuit, let's say that this is a battery, right? This is a resistor, right? And this is a switch. Let's remove all the switch and all, right? Let's analyze the circuit from here and then come back to the same place, right? What will happen? This battery will change the potential and this a resistor will create a potential drop or something, right? But what will happen if you are analyzing the entire loop? That means you start from here and you come back to the same place. You start from here and you come back to the same place, right? If you complete the loop, if you analyze the whole loop, the change of potential that you will observe will be 0, right? Because you came back to the same place, whatever change you will observe, that is going to be 0, right? You came back to the same potential because, right? So what will happen? We can say that due to all the effects when we are analyzing a loop, right? That means we start the analysis of a loop from a place and we come back to the same place. Whatever potential rise we will observe, the same amount of potential drop we will also observe. So the potential rise and potential drop that we have observed is same, right? The potential rise and potential drop that we have observed is same, right? So this is the Kirchhoff's second law, right? This is one way of writing Kirchhoff's second law. This is also the same thing written in a different format. You will understand that right now in just few seconds, right? Try and understand it. Now, to understand one thing going further, when we are talking about Kirchhoff voltage law, KVL, one thing you have to talk about is how, the way we analyze it will decide whether the resistor will give us potential drop or potential rise. Potential rise across resistor, yeah, you can get it. Try and understand it. When we are analyzing from lower potential to higher potential, we are getting a potential rise of potential rise, right? No. And when we are analyzing from higher potential to lower potential, we are analyzing a potential drop, right? So try and understand it. This is a resistor and the current is flowing in this direction through that resistor R, right? Current flows from higher potential to the lower potential, right? Now, while analyzing in the loop, we are analyzing this resistor in the direction of current. This is the direction of analysis, not the direction of current, right? We are analyzing this resistor, right, in the direction of current. So, because the current is flowing from higher to lower potential, current is moving from higher to lower potential, and we are also analyzing it from higher to lower potential. So, what will we observe? Potential rise or potential drop? We can say that while following the direction of current, we will observe a potential drop because we are moving from higher to lower potential, right? So how much potential drop you will observe? We can say IR, you will observe a potential drop, right? Now, if you are analyzing the same situation, but in this direction, right? Again, the direction of current, this is not the direction of current, this is how you are analyzing it. You are analyzing the current flowing in the resistor opposite to the flow of current, right? So you start your journey from here and now you move towards this way, right? So you are moving from lower potential to the higher potential. Because you are moving from lower to higher potential, you are observing a potential rise. Potential rise. So what is happening over here? You are moving from lower to higher potential. You are observing a potential rise. The same value of potential rise will happen. Yes or no? So across a resistor, you will observe a potential rise or drop, depends upon in which direction you are observing the potential rise or drop, right? Let's move on, talk about the next idea, right? So the same thing is there, right? You have a battery, right? And the battery again, across a battery also you can analyze. While the analysis across a battery, you can also get a potential rise or potential drop. How can you get that? Let's say that this is at a higher potential, this is at the lower potential, and you are analyzing in this direction. While analyzing through a loop, you go through this way to that way, right? And since you are moving from a higher potential to a lower potential, since you are analyzing it in this direction, you will say that I have observed the potential drop, higher to lower potential drop. And if the EMF of the battery, let's say, is E, right? So right now you have observed a potential drop of E volts, right? Now, if you are analyzing it in this way, right? If you are analyzing in this way, right? So you are moving from lower potential to higher potential, lower to higher. So what will happen? You will observe a potential rise of E volts. I believe you got the idea, right? Depending upon the way you are analyzing it, you will get the potential rise or potential drop. Let us have a look at this particular situation and try to, solve it. All right. So here we have it. Right. Here we have this particular thing. Right. And always remember that whatever potential rise you will observe has to be same as potential drop if you are analyzing till the same point. You come back to the same point, right? Look at this particular question, right? Here you have this situation going on with you, right? And you have to solve it. Now you have to talk about two things, my dear kids. First of all, you have to talk about how much current is flowing through R1, R2 and R3. So there are three resistances, R1, R2, R3. How much current is going to flow through them? The expression for those values of current you have to figure out, right? So this is the first thing you have to figure out. Currents through R1, R2 and R3. All these numericals I have chosen so that you get absolute concept clarity. You need to find the values of current through R1, R2, R3. The second thing we can find out is what will be the potential difference VB minus VA or VA minus VB in this situation. So what is going to be the potential difference, right? So if you do that, like the idea of KVL will be very, very clear with you, right? So let's have an understanding of this thing. So in the KVL, we will analyze the loops, and because we have two loops, we will analyze both of them. So right now, let us say that here the current is flowing in this way. Let's say the value of current is flowing is X. Some current will move this way, the other current will move in the other direction. Let's say the Y current is moving this way. Remaining current X minus Y is following this path, right? So let us try and understand that. So this is the first loop and this is the second loop, right? We are analyzing the first loop in this way. We are analyzing the second loop in this way, right? So when we analyze the loop number 1, right, we are analyzing the loop number 1. So what will happen? Again, you will say that the potential rise you will observe should be same as potential drop in the entire loop, right? So while analyzing in this direction, you are going through this battery in this way, right? You moving through this battery this way, through this resistor this way, through this battery this way, and through this resistor this way, just like that. You are moving like this, right? So while moving across this battery, you are moving from lower to higher, negative to positive, lower to higher. So when you're moving from lower to higher across this battery, you observe potential rise. So write it on this side, E1, right? And now when you moved across this resistance R1, what did you get, right? When you moved across this resistance R1, what did you get? We can say we are moving in the direction of current. Current is from higher to lower potential, higher to lower. So we will observe a potential drop, right? How much potential drop will you observe? X into R1. So write it on the drop side. Okay. Now what is happening? When you move at this place, you are moving from higher to lower. If you are analyzing in this direction from higher to lower, E3, you will get the drop. So again, write it on the drop side. Okay. And while analyzing this resistor R3, you are moving from in the direction of current. Current is moving this way, and you are also analyzing in the same direction while moving in this direction, right? So higher to lower, that is also you are getting a drop. How much drop you are getting? We can say potential drop is the value of current is X minus Y into R3, right? This is the value, this is the first loop, this is the equation that you get in the first loop, right? You will have some values of E1, R1 and R2, just put the values and you will have an expression between X and Y in the first loop, right? Similarly, in the loop number 2, right? In the loop number 2, you can also analyze and get another equation, right? Let's try to make the equation first. So what will happen? When you analyze, when you are analyzing in this direction, you have to analyze this resistor in this way, this battery in this way, and then this one in this way, and this battery in this way, right? So over here, you will get a rise or drop. You are following the direction of current. So across a resistor, in the direction of current, you will get the drop. How much? Y into R2. Y is the current, and that you will get potential rise equals to potential drop. So drop, how much you will get? I into R2. So Y is the current and the resistance is R2. This is the drop you are going to get, right? Across this one, you are moving from higher to lower like this. So higher to lower, you will get drop. Again, you will add it on the drop side, E2, right? Across this one, you will get, you are moving from lower to higher, the current is moving this way, you are analyzing it in the other direction. So lower to higher, you will get the rise. How much? Current is X minus Y and value is R3. So X minus Y into R3, this will go in this direction, right? And then you are analyzing this battery again from lower to higher, E3. So you will add it on this side, E3, potential rise side, okay? And that you have to equate. So again, you will get another equation in X and Y in this format, right? Just put the value of E1, E2, R1, R2, whatever is given in the question, right? You will get two equations in X and Y. Solving them, you can find the values of X and Y, right? X is the value of current flowing through R1, Y is the value of current flowing through R2, and X minus Y is the value of current flowing through R3. So by doing this, you have figured out how much current is flowing through R1, R2, R3, right? No problem with that. Now you have to find VA minus VB. For VA minus VB, you can simply do the same, analysis, right? You can just start from A and just move towards B. So in the second part, you have to find the VA minus VB. Start from this point, VA, right? Then you are moving from positive to negative. So what will happen? Potential drop you will observe. How much potential drop you will observe? Right. Right now you can easily get that. You see that it is E3, right? So you will get higher to lower, so that clearly you will analyze a drop, right? VA minus E3, and then across this one, so current is X minus Y into R3, right? That equals to VB. I believe the idea is very, very clear. So you have already, you know, the value of E3 will be given in the question. X and Y you have already calculated. R3 is some value of resistance, right? And of course, VA minus VB can be easily figured out in this particular way, right? I believe there is no problem in this one, right? It's a very simple concept of Kirchhoff voltage law. And you can always remember that it is simply based on law of conservation of energy, right? So after doing the Kirchhoff voltage law and Kirchhoff current law, you have seen that following the problem solving with the help of nodal analysis or Kirchhoff current law is much, much easier, right? And it is also a lot versatile as well, right? So after doing all that, we can now move on to the next part, which is part number 3, right? And start talking about it. So here we will be discussing in brief about the internal resistance, potential difference, and EMF of the cell. This concept is not asked many times in the paper, right? So we will be discussing it in a brief. Wheatstone bridge is also a very sometimes it is asked, right? Very rarely these questions are asked, but since it is there mentioned in your syllabus, that is why we will cover it. We will only give it a time that is, going to just cover the syllabus, right? And give you enough overview of the concepts that are going to be there in your syllabus, right? So let us do that. So here we have it. What do you mean by EMF of a cell? What do you understand by EMF of a cell? So my dear kids, if you have a cell in front of you like this, right? So since it is not connected to the battery, right? It is not, discharging any current because current needs a closed circuit, okay? So if the current is not flowing in the circuit, right now if you try to measure the potential difference, it will give you some value, right? So this is the open circuit value, this is the maximum possible potential difference you can have, right? But as soon as the current starts flowing, what will happen? When the current is flowing through this one, and now think about it, it will flow through a loop, right? So while the charge is trying to go through this one, this path, currents are flowing through this way and then they are following through this path, right? So the flowing charges will experience resistance through the material of the battery itself, right? So you see that apart from the external resistor to the battery, apart from the, this is the battery, right? This is the external resistance. So when the current is moving like this, so this flowing current is going to move through the battery itself, right? So apart from that, the charges that are flowing, they will feel the resistance due to the external resistance. They will also experience resistance due to the material of this particular battery itself, right? So the resistance offered by the cell itself will be called as internal resistance, right? So when the cell is when in a real world, when a cell is connected to the external power, external resistor, right, it will not offer the EMF across the terminal. The potential difference it will offer will be slightly lesser than the EMF, right? So if you check the actual open circuit voltage, it will be 1.6, 1.7, but when it is connected to the circuit, it will be much lesser. Why so? Because when the current is coming out, it has already incurred through the internal resistances of the battery itself, right? So in many books, they are using this notation. Instead of using the battery like this, the real battery they are representing like this. The real battery they are representing like this, okay? Yeah, like this. So they are connecting a small resistance. This resistance is there inside the battery. So they use a dotted line just to show that this resistance is a part of a battery. All right. I hope the idea is very, very clear. Right. So if you have any question or confusion, you can definitely ask me, right? This is what going on in this particular situation, right? The energy given by the cell, or in this situation, EMF of the cells, right? So let's move on and talk about the next idea, right? This is the internal resistance, small r. EMF of the battery is E. The potential that you will get at the terminals of the battery is called as the terminal, or the terminal voltage, right? VO, right? And this is the external resistance, capital R. Small r is the internal resistance of the battery, right? So right now you can say that the potential difference across the terminals of a cell, while it is not giving any current, is called as EMF of the cell, right? So when it is not giving any current, it is basically in the open circuit. In that particular situation, the potential difference you get is EMF, right? But as soon as you connect to the external resistance, right, it will start offering you a lesser value than EMF. That is because it has already an internal resistance, right? So EMF of a cell depends on the nature of electrolyte and metal of electrodes and all. Internal resistance, I have already told you. What is the resistance? The resistance offered by the battery itself is the internal resistance, right? Terminal voltage is the net potential difference you get out of the battery, right? So you see that EMF minus potential drop caused by the internal resistance. So I is the current coming out, let's say. So I into small r will be the potential drop caused by the battery due to its own resistance. So E minus IR you will get at the outer terminal while the battery is discharging. E minus IR is going to be the potential difference that will be offered by the battery to the external power circuit. All right. So I believe the idea is very, very clear. Right. So the current in this situation will be E upon R plus R. No problem with that. Now look into the Wheatstone bridge. What is happening in this situation? So here you have these four resistors connected in this particular fashion, right? And across these 2 points, we are connecting a galvanometer, right? We found out that if these resistors are following a certain ratio, then we can balance the galvanometer, right? So what is happening? For a balanced Wheatstone bridge means there is no deflection in this arm, means this point and this point have to be in the same potential, at the same potential. Otherwise, if there is a potential difference, the galvanometer will deflect. The current will flow in this arm, yes or no? If there is a potential difference between B and D, because there is a potential difference, there will be flow of electricity, right? So electricity will flow and the galvanometer will deflect. We don't want the galvanometer to deflect. So what will happen in this arrangement of 4 resistors? The galvanometer is balanced, means it is not deflecting. It is not showing any deflection. Zero deflection is there, right? So what will happen? Here, right now the current through the galvanometer is zero. The current through the galvanometer is zero. Wheatstone bridge is balanced, right? So in this specific situation, we have observed that the current, because there is no current flowing in this way, right? Galvanometer is balanced. There is no current flowing this way. So whatever current goes here in this path, zero current flows. So all the current has to move in this way only, right? So whatever current starts over here, none of that is divided. All of that follows through. So I2 and I4 has to be same. Similarly, I1, none of that goes the other way. I1 and I3 has to be the same, right? In the case of balanced Wheatstone bridge, right? So if you simply apply the Kirchhoff's law in the available loops, so you will find that these equations are holding true, and by the simple analysis you will say the ratio of resistances or the ratio of resistances of adjacent arm is same. R1 is to R3, R1 is to R3, and R2 and R4, they are going to be same. Or you can write down the same thing in this way as well. R1 and R2, these arms, the ratio of these arms and these arms, the resistances of these arms are going to be same, right? So this is only happening, this is only going to happen in a balanced Wheatstone bridge, right? Okay. So over here you have another format of the same Wheatstone bridge. All three formats are just representing the same Wheatstone bridge. Try and understand that. If they are saying that it is a balanced Wheatstone bridge, X and Y have to be at the same potential and the resistance R5 will not get any current at all, right? And in such situation, R5 will be a redundant resistance and you can remove it from the circuit, right? Redundant resistance and you can remove it from the circuit. I believe the idea is very, very clear. Same thing goes on with this case as well. R1, R3, R2, R4, right? Same thing, X and Y are there. R5 can be removed from the circuit, right? Okay. And similarly, in this situation as well, between these 2 points, if you just focus on these 2 points, right? If these ratios are holding true, this resistance will not get any current and it can be removed from the circuit totally, right? So let's move on and talk about the next idea. Right, look into this situation and try to solve it. Here what is happening? Look into this situation and try to solve it. What is happening? The equivalent resistance between A and B of the network shown in the figure. Between A and B, what will be the equivalent resistance, right? So here, if you try to look into this situation, look at this ratio, right? R and 2R, the ratio is 1:2. And look into this, 3R and 6R, the ratio is 1:2. Because the ratios are holding true across this point, so what will happen? Across these two junctions, this resistance will not get any current and it is a redundant resistance, can be removed from the circuit. So by removing this resistance, the remaining circuit will be like this. R and 2R, right? And similarly, this resistance is removed. So we can just extend it, 3R and 6R. Now you see that R and 2R are in series, so 3R and then 2R and 6R in series, so 8R, 3R and 8R are going to be in parallel. Just find the net value of resistance of these two things, right? So I believe the idea is very, very clear. There is no confusion in that particular part, right? All right. Okay, this one is 3R. This one is 3R, not 2R. So R and 3R are 4R, 4R and 8R are going to be in parallel, whatever. Right, so this is it. Now, combination of cells is also there. Sometimes, let's say, when we are utilizing the cells, let's say in this remote, right, we are not using one cell because one cell is not enough. It is doing a lot of different things. So we use multiple cells, right, multiple cells in it. So right now, what we are doing is we are doing the combination of, cells. So combination of cells also not just adds up their EMF, it also affects the net internal resistance of the arrangement. So here, if I'm adding in this way, all the polarities are aligned with one another, positive and negative, positive and negative. This is the kind of combination we are doing. In this situation, EMFs are added up. So just like that, if this is one battery of 1.5 volt, right, the positive of this battery is connected with the negative of the other one. Right. Now across this terminal, the net EMF is E1 plus E2. If this one was offering EMF E1, this one was offering E2 alone. But when you put them positive and negative side by side, now the whole thing is offering E1 plus E2. Similarly, now the whole thing is offering E1 plus E2 plus E3. I believe the idea is very, very clear, right? Here what is happening, positive is connected with the negative, positive connected with the negative, and E1, E2, E3 are the EMFs. So the net EMF is going to be E1, E2, E3, summation of these three things. And R1, R2, R3 are the resistances. So now the resistances are also added up because all three of them are in series, right? Similarly, in the parallel combination, this relation holds true. Net equivalent resistance is this, right? So yeah, this is how we figure out, right? Now the next concept that is also based on the concept of Wheatstone is Metre Bridge. So Metre Bridge is going to utilize the combination of four resistances, although you will not see the actual full resistance, but if you observe it clearly, you will easily find that those four resistance will be visible to you, right? Now Metre Bridge is a very versatile instrument, right? Let's have a look at how this functions, right? Okay, so it is a setup that can help us measure the unknown resistance. So let's say that we have a wire, right? We just randomly found a wire somewhere on the road and we don't know the resistance of this wire. So how can you find out the resistance of this unknown wire? We can say with the help of Metre Bridge, we can find out the resistance of unknown wire, right? Acha, while using the Metre Bridge, you need to know very clearly that Metre Bridge can deal with one unknown wire only, right? This is the wire of unknown resistance, right? And there has to be another wire of known resistance as well. So we'll talk about that. Okay, so here you see that this is a copper plate, this is the copper plate, this is the copper plate, and between these two terminals we have a wire of 100 centimeter, that is 1 meter, which is why it is called as Metre Bridge. So 100 centimeter or 1 meter, right? Okay. Now this is the copper strip, as you can see, right? But there is a gap over here, right? So the circuit is not completing right now. Good. So we need to complete the circuit somehow, right? Okay. To complete the circuit, we will connect something here and connect something here, right? So how to do that? Let's have a look into this situation. Right now, across A and C, so this is the wire already, 100 centimeter wire. Across A and C, you are applying a EMF, right? Okay. Now, let me just connect it side by side. This is one plate, another plate. This is another plate. All right. These are all the plates you have. All right. Now, between these 2 points, this is 100 centimeter. The wire is there. 100 centimeter wire is there, right? Okay. But there are gaps, and now we need to complete it. Now, as I have told you, you need to have an unknown resistance, and you can only have one unknown resistance. Let us say that the unknown resistance you need to know the value of, you are connecting it over here, right? And there is one more known resistance that you can connect somewhere else. Let's say that you are connecting a known resistance over here, and the value of known resistance is S, right? But see that there is no current as of now. So to get the value of current, we have external power supply, right? So this is the external power supply we have, EMF E, right? So this is what we are offering, right? This is a meter scale, just to measure things up. It is going to help us in measuring things. All right, so this is 0 and this is 100 centimeter mark of the meter scale. Okay, now what is this? This is the galvanometer, right? And you see that we are going to use this attachment, galvanometer, and then they will be like this, right? So this end is called as jockey. Jockey is a simple pen-like structure with a metal tip. Other end is connected with a wire, right? So this is the jockey, and this is connected to the galvanometer, and the other terminal is free, right? So what will happen? We are connecting two terminals, one this point, right? And we have a galvanometer, right? Okay. And the other terminal, other end of the jockey is free, right? So what are we trying to do? We are taking the jockey and we are moving it over here, right? We are taking the jockey, we are touching at a different points on the wire, this 100 centimeter wire, right? Let us say that at a distance x from the point A, galvanometer had no deflection at all, right? So the remaining distance will be automatically 100 minus x, right? At a point x, we got no deflection in the galvanometer. Now think about it, by the Wheatstone bridge, if you imagine this part of the wire is serving as one resistor, right, and the other part is serving as another resistor. Now you have four resistors in front of you. Why? This part, this part, this part, and the second part of the wire, right? Now, since the galvanometer is not offering any deflection, that means the galvanometer is balanced and this Wheatstone structure is balanced. So, R and this resistance, S and this resistance, the resistance of this wire has to be in the same ratio, right? So, let us do that. R and S, the ratio of these two things has to be in the ratio of these two elements, right? So you know that resistance of this part is rho L upon A is same, rho is same. So resistance is in a ratio of length, L upon 100 minus L, right? So you do that. So you see that resistance, the unknown resistance R is going to be L upon 100 minus L into S. So basically, if you are balancing the galvanometer at a length L from end A, if you are balancing the galvanometer at a length L from point A, what we will get, we will say that the known resistance will be L upon 100 minus L into S, right? So this is going to be the known resistance, right? That's pretty much everything, right? Okay. Now, after completing the meter bridge, let us talk about the last concept as well. Here we are going to discuss the concept of electrical energy and power. Let's discuss that as well. So, the power is the rate at which the energy is consumed or the work is done. For example, you have seen a 100-watt bulb and then you have seen a 10-watt bulb, right? So 100-watt bulb is consuming 100 joule per second and 10-watt bulb is consuming 10 joule per second, right? So you have seen the star ratings, right? 5-star rating appliance and all. So yeah. So here we have it. What is meaning of electrical energy and electrical power? So power is basically the rate at which the work is done or the energy is consumed, right? Here what is happening? When we have a resistor, so resistor is an element that cannot do any meaningful work, right? So resistor will not start moving for you when you apply the electrical energy across the terminal. So what will it do? Whatever energy you are giving now, that will be wasted in form of heat, right? And how much heat will be created? For a value of current I, the heat created will be VIT or I square RT, right? I believe the idea is very, very clear. The value of heat created will be I square RT, right? So just put the value of I, V equals to IR, right? So I is going to be V by R, right? I is going to be V by R. Just put the values and you'll get the value of heat or you say the energy that you have invested in this particular situation, V square by R into T, right? So if you take the time over there, the remaining term will be the power. So if you take the time over here, VI is the power. Take the time over there, I square R is another expression of power, or time over there, V square upon R is also power, right? All right. So yeah, these are the expressions for power. The unit of power is watts, right? So this is a very simple idea, right? Okay. So that's pretty much everything about the chapter of current electricity here we can say, right? And we have understood each and every idea in great detail in this particular video. Now, what I'll suggest you, just go through the, whatever section is, you still want more clarity on, just go through that section again. And after this, just download the DPP from the link given in the description and practice it, right? Because practice is something that is required from your end, right? And I've chosen the question so well that it will help you out in, like in the final NEET exam as well, right? So on that note, let's keep this lecture till here only. I'll see you there in the next class with few more interesting concepts and some amazing theory, right? So till then, take care and bye-bye. I'll see you there in the next class.